Well, good morning, everyone, and welcome to our second day of the U.S. DOT AI Assurance Workshop. This is presented by the U.S. Department of Transportation Office of the Assistant Secretary for Research and Technology in collaboration with the Federal Aviation Administration. My name is Stephen Zoff, and I'm the Acting Director for the Highly Automated Systems Safety Center of Excellence. We had a really fascinating series of discussions yesterday, and I want to thank all of our guests and our speakers for their contributions. And we have another great series of talks prepared today. Before we get started, I'd like to turn it over to Denise Bakar for a few logistics. Denise?
Hi, everyone. Welcome to day 2 of the workshop. A couple of items I want to address at the top. So the views and opinions expressed in this presentation are the presenters and do not necessarily reflect those of the US DOT. The contents do not necessarily reflect the policy of the US DOT either. We don't endorse products, manufacturers, or outside entities, and any trademarks, names, or logos that appear are for informational purposes only and not intended to reflect a preference, approval, or endorsement. A couple of ground rules for today. So please remain muted and with your video off unless you are a moderator or speaker. You're welcome to drop questions in the chat window anytime throughout the workshop. This workshop is being recorded and transcribed. And please note that this is a public event, so try not to share any sensitive data or information, and so we can maintain confidentiality and respect. Please also be concise. Avoid using any undefined acronyms, just to help general understanding. We have a lot of participants in this workshop, so be concise. Avoid acronyms as much as you can unless they are defined. And if you have any questions, feel free to reach out to me at denise.bakar@dot.gov. I'll now hand it over to Haas COE Deputy Director and Chief Scientist, Dr. Taylor Lochrain, and he'll provide an overview of the workshop today.
All righty, well, good morning, everybody. Welcome back, day 2. We got a huge agenda, packed agenda for this afternoon. What a wonderful day. For those of you that joined us yesterday, I hope you got a lot out of the conversations we had when we talk about AI safety and governance, we talk about AI risk management and mitigation, as well as the AI data assurance. So if you could look on Thursday's agenda, which is presented right here on the slide in front of you, we're going to kick off today with Brian Cronin, ITS Director, Joint Program Office, followed by the panel, an awesome panel that's going to dive deep into the AI assurance research needs and priorities. So we hope this could be very dynamic. We're going to have a great morning, great afternoon for those on the East Coast. And then we're going to dive into 2 technical sessions as part of what Dr. Wafang presented yesterday in our AI assurance framework, both data time assurance, or design time assurance, pardon me, and operational time assurance. So these are very important areas and components in this process as we start to dive deep into AI assurance and we start to share this collective learning across our academic partners in this space. And then in the afternoon, we plan to do a reflection of what we learned over the last 2 days with a panel of folks, followed by a wrap up and next steps on what are the next opportunities we see in moving this work forward together as a community. So again, I just want to say, my name is Taylor Lochrain. I'm with the Haas COE, which stands for the Highly Automated Systems Safety Center of Excellence. Just for those of you that weren't with us yesterday, our office is really focused on supporting our operating administrations within the DOT on reviewing, assessing, and validating highly automated systems for safety. And so this is a very important area, we believe, when we talk about AI and we talk about AI assurance. It falls into that assessing and validating component of our role within our office. And we're working strongly with our OA partners in helping where we can, because this is an emerging topic, emerging area. A lot of the foundational elements of this program have been around for a while, but as it all starts coming together, I think as a community, there's a lot of work we can do to really escalate this work and ensure that when we move these products into the community, that they're going to be operating safely. So with that, we're going to go ahead and start off with our first poll question of today. So I'm going to pass it over to Haley, who's going to jump off with our first poll question.
Great. Thank you, Taylor. Okay, let me take the screen. If you were here yesterday, you will be very familiar with this process. If you were not here yesterday, welcome, and we hope you will submit your responses to some of our polls today. They're interspersed throughout the workshop. So if you just go to menti.com, you can type in the code 81205112 or use your phone for the QR code that's shown on the screen, and it will be on every question slide as well. So don't feel like you have to save it. So I'll give folks just a second to use this to get back to our poll. If you weren't here yesterday, you will see 8 questions that you'll have to skip from yesterday that won't be available to you because they are now closed. So I'm just giving you some warning there. We're going to start with question 10 today. So let's move to it. Okay. So how confident do you feel applying the AI assurance concepts covered in yesterday's workshop if you were here yesterday? If not, you can say I did not attend day 1. So let me start my timer. Okay. And I want to emphasize that your responses are anonymous to this. The first question I'll ask you again, if you weren't here yesterday, is your organizational affiliation. So if you could please answer that. And if none of the options speak to you, you can type in the other option. You only have to answer that one time. And we highly value your feedback, and it will remain anonymous. So I see the numbers ticking up. Awesome. This is our good warm up for the day poll.
Yeah, and if I could add, Haley, while we give some folks some extra time here to answer the question, just want to highlight that these questions that we're asking are fully anonymous. We don't know who asked these questions out of all you all, but we're just trying to understand a little bit more about the AI assurance space. We plan to share all these results at the end of the conference, so you'll be able to see the numbers and use these questions to help maybe drive some of the areas that you guys want to drive forward in AI assurance. I just want to highlight that these questions we're asking, we're going to share the responses at the end, but they're fully anonymous, and they're just going to help us get an understanding of where we're at in this space. Thank you.
Great, thanks, folks. I'll keep it open a little bit longer because I know it takes a minute to get to it. But here we have our results so far. So we have somewhat of a mix, but somewhat confident in the concepts covered yesterday. So that's great. That's probably a good place to be since we're continuing the conversation today.
Yeah, so we're 2 out of 4 of our main components for AI assurance for this program, and this is a very good sign that we're learning. I think we're all learning together. I think there's a lot of conversations we had yesterday, a lot of dialogues from our presenters in the panel that really probably informed our knowledge. And I hope that this can start more conversations and more partnerships across the community so we can continue to dive deep into this research space of AI assurance for safety. So with that, we're going to go ahead and we'll keep the poll open, as Haley said. Thank you, Haley. And we'll go ahead and we're going to move into our keynote speaker, Brian Cronin. So we'll pull up that slide, and I'm going to go ahead and introduce Brian. So Brian Cronin is the Program Director for the Intelligent Transportation Systems Joint Program Office, which we refer to as the ITS JPO. He provides strategic direction for the research and development of ITS. Brian provides advice to the Assistant Secretary for Research and Technology on ITS policy, strategic program direction, and budget allocation. Prior to this role, Brian served as the Director for the Office of Safety Operations Research and Development at the Federal Highway Administration for the past 5 years. And 2 years prior to that, he was the Director for the Office of Operations Research and Development. In his most recent role, he provided executive leadership and guidance for improving and advancing transportation safety and operations-related technologies and innovations throughout research, development, and testing. Brian provided executive leadership in Federal Highway's involvement in the Intersection Safety Challenge, development of a vulnerable road user research plan report to Congress, and establishing a new center of excellence for new mobility and automated vehicles. Brian's guided the development of the Cooperative Driving Automation Research Program and V2X research efforts. And prior to his appointment to the SES, Brian served 11 years at ITS JPO, with the last 8 of those 11 years serving as the ITS research team leader. In this position, he provided strategic leadership and the direction in the development of ITS solutions to improve transportation, mobility, safety, and environment. Brian's provided technical leadership for the development of the Connected Vehicle Research Program and the Secretary of Smart City Challenge. Prior to joining Federal Highway in 2003, Brian served as an advanced public transportation systems team leader within Federal Transit Administration, where he oversaw the research and development of transit-related ITS technologies to improve transit operations. Brian holds a master's degree in civil engineering from Texas A&M University and a bachelor's degree of civil engineering from Virginia Tech. Brian is also a licensed PE in the state of Maryland, so PE, go PE, folks. Brian's also just recently, big news, celebrated his 25th anniversary with his wife, Lisa Lacrosse, and his two girls, Lucy and Julia. And Brian enjoys camping, kayaking, hiking, swimming, biking, golf, and talking about all things technology and attending workshops like this to engage with our community. So Brian, thank you so much for being here today, and we look forward to your keynote speech.
Hey, thanks, Taylor, and thank you, everyone. Thrilled to be here today with my DOT colleagues and all these amazing stakeholders. What a great event yesterday. So getting right into it, roadway safety is a national problem in the United States. In 2022, there's approximately 42,795 fatalities on our roadways. The safety problem can seem insurmountable, and according to the World Health Organization, the U.S. is woefully behind our peer countries when it comes to safety. So when we think about the role of AI and technology, I really want to drive home the need and opportunity that technology has to impact safety. So what is the U.S. DOT doing? We're committed to reducing the number of roadway fatalities to the only acceptable number, which is 0. We issued the National Roadway Safety Strategy outlining the department's comprehensive approach. We added in the first update really specific requirements about ITS and innovation and technology as a way to approach and improve safety. The NRSS works to build and reinforce multiple layers of protection to both prevent crashes from happening in the first place or minimize the harm caused to those when crashes do occur. The NRSS has adopted the Safe System approach, which takes a holistic view of the road system and anticipates that humans do make mistakes, and second, keeps impact of the human body at tolerable levels. With the Safe System approach, there's need to explore how research elements across safer roads, safer vehicles, safe road users, speeds, and post-crash care interacts collectively, and how technology could play a more significant role in improving road safety. I like to think about this as we can design a separated bike lane with plastic pylons to separate it, but every now and then a vehicle can drive into that lane and across that pylon. So if we had collision warning technology like V2X, you could have another layer of defense to help provide warnings both to the bicyclist and the driver. So we need to think holistically about the system and the role of technology. So US DOT recognizes the promise of AI in achieving transformative improvements to safety, efficiency, equity, productivity, and sustainability. AI has many practical applications in transportation, from planning to real-time operations. The transportation system is flooded with data right now, and that data continues to grow, and it continues to be reliable and accurate for the most part. We need to really think about that. So how can AI tools be used to help turn that data into information that operators and road users can use to make better decisions? Some of the data will be used for planning, and sometimes in real-time decision-making and in warning systems. So for example, Taylor mentioned my involvement in the Intersection Safety Challenge. We can detect pedestrians and other vulnerable road users and prevent conflicts. So last year, the US DOT announced the Intersection Safety Challenge to leverage technology and improve safety at scale, looking at data fusion, existing sensors, and how important we use AI and machine learning to reduce costs and implement high-value applications at scale at intersections to save lives. So data fusion will emerge in low-cost sensors can be deployed at intersections to detect vulnerable road users, and we can fuse that and use AI and information from vision sensing and technology and radar and LiDAR, and then predict when there's going to be a conflict and when a warning is needed. And so we were really excited last year at TRB in January, the Transportation Research Board, to announce 15 Stage 1A winners that had tremendous ideas and concepts. They have now entered Stage 1B to develop out the concept and in particular be able to determine and use AI on an existing data set that we created to predict and analyze when and if to do a warning. Successful applications to the Stage 1B will be announced at the end of the year or in January of 2025. And then we hope to issue a broad agency announcement to deploy these with our state and local partners and really show the value of AI and advanced technology for intersection safety. But AI doesn't just stop there. We can improve traffic flow by predicting queue buildups through real-time signal optimization. We can enhance transit signal priority. We can improve freight mobility or optimize load or truck movements. AI tools can be used to optimize curb management and minimize mixed use of vehicles, pedestrians, looking at accessibility of the curb at busy intersections. Earlier this year, we announced the Complete Streets AI initiative, and if you were on yesterday, Dr. Hampshire talked about this. This is a $15 million multi-phase effort to look at how funding small businesses can utilize AI to help create tools for state and local agencies to better design and analyze where they might implement a complete street network. Complete streets are streets that are safe for all users. They consider design, technology, and really help improve the safety of these streets for everyone. So there's a data gap right now, and we need to understand creative methods to look at national data sets using novel and scalable approaches to data science, to use big data, AI, computer vision to help us understand where complete street networks can be built out in our cities. Cities need to understand the opportunity, and the data is there. They just may not have it yet to be able to better plan and design where to implement. So we're looking through this challenge, through this SBIR, Small Business Innovative Research Program, to create a decision support tool that can be interactive and help users visualize and understand where they can make complete street improvements, whether that's designing and implementing a bicycle lane, adding V2X, vehicle to everything communication, so you have a connected street, any number of different technologies and opportunities to build out that design. So these are some of the ways that communities are using AI. We know that businesses are out there now, universities are conducting research, many of you here today. So there's been unprecedented growth in AI algorithms and tools. The community has access to many vendors and products at their fingertips. And agencies need to use AI to address various different needs, from safety critical decisions to planning and outward. But we need to trust that the data is there, the results are timely and accurate, so we can bring transformative benefits, but we could also cause harm or pose a threat to national security. So if these systems are not trustworthy, President Biden issued an executive order in October to address national needs for providing oversight of AI development and use. The AI executive order advances an urgent, coordinated federal government-wide approach to development and use of safe, secure, and trustworthy AI. The urgent and critical need to develop and use AI responsibly, free of discrimination, bias, fraud, and disinformation. AI systems should empower the workforce and not stifle competition. AI systems should be trustworthy, secure, and protect individuals' privacy. This workshop is focused on AI assurance, which ensures the AI systems produce output and outcomes that are reliable, verified, accurate, explainable, fair, secure, and protect the privacy of individuals. AI holds enormous promise, and we look to you to help us achieve that. But we require coordinated actions from the government, the public sector, academic and research communities, and the industry to ensure trustworthiness of the data, the algorithms, tools, the design, implementation, and use of AI. We had a great event yesterday, and some of the key themes that came out, I want to call out. We need to look at training data for AI systems. The data must be unbiased, representative of the operational domain, and must include critical edge cases, not just the common situations. Stakeholder perception. We need to do public education, workforce development, and dispel misconceptions, either when stakeholders are skeptical or mistrustful of AI systems or have exaggerated expectations of the capabilities. Standards. Developing, testing, and implementing of standards for AI data performance in governments continue to be a priority for trustworthiness and responsibility. AI technology continues to evolve rapidly, requiring an active role in evaluating and updating applicable standards. So with my last few minutes, I'd like to tell a story and talk about how the department, through our National Vehicle to Everything Deployment Plan, really could use and think about how connectivity can really harness the value that AI tools can bring to data. If we think about now having the ability to communicate in real time through V2X, whether that's using the 5.9 spectrum and the 30 megahertz and cellular V2X, or using network V2X or cellular systems to longer range communication, we must have accurate and reliable data to communicate. And deciphering through all that data and information, we can use AI tools to help with that. So let's harness and get ready to implement a national V2X network and plan, but let's have the data and tools so that we have excellent information to provide reliable and accurate collision warning, to provide trusted traveler information, to help operate the system better. I thank you for your time. I look forward to hearing discussions on what key R&D elements are for addressing the AI insurance needs. I'll turn it back over to Taylor and the team, and I appreciate you spending the time with us to help us make this AI program amazing.
Awesome. Thank you, Brian. That's so informative. I think one thing you said during your conversation with how AI tools can turn data into information for decision makers. And we learned a lot about that yesterday during our data assurance a technical session. So I find that really important. And I think some of the pieces that are going to help with that is what we're going to talk about this afternoon when we talk about design time and operational time assurance. And also yesterday, I thought was very interesting during the risk management session, we talked a lot about how V2X could leverage AI tools in kind of using some of that data to improve safety or decision of some of those tools. So a lot of this is just emerging so quickly. And so, Brian, I have one question for you. In your interactions with the stakeholder community, like what are you hearing about when they talk about AI for ITS?
Hey, great question. I think right now it's a tool and people have been using it for years. It's not a new tool. It's just now we have the compute power, we have the data analytics power, we have the cloud, we have all these capabilities that make AI happen in real time. There are so many agencies that are now also looking from a safety perspective. Think about if you have sensors on your roadway and you apply AI tools, you can understand when pedestrians aren't actually crossing at the crosswalk, but are crossing in the middle of the street or doing different things so you can better think about design. We can use it for technology solutions for warning. So I think the main thing I'm hearing is the community's ready to deploy at scale now and use these tools. We need the information to help ensure that there's trust, there's reliability, and that we know that the recommendations coming out of these tools can be used in real-time operations and management and real-time safety solutions. You don't want to provide a life-altering collision warning safety message and not think you can trust it. And so these tools are there. We need them to be reliable and accurate, and we want everybody to start deploying.
That's great. Yeah, and I think that's a lot of what we were hearing, when we talk about AI assurance. I mean, Dr. Wolfgang Yu gave an amazing definition, up in front. We have to look at these systems and how we can trust what they're saying and that we can evaluate that the output is something we could use. I think that's important. When we get to that milestone, we've done the checks and balances, we've assessed these systems. These systems can be very powerful in helping us improve safety across all modes of transportation. So, Brian, I want to thank you on behalf of the team here, on behalf of all of us that are participating in this workshop for joining us for this keynote session. And we will move forward now to the next panel session with Jason John Michael. Thank you, Brian.
Have a great day.
Thanks, Brian. And we'll move over to Jason John Michael. We're going to jump into our panel on AI assurance research needs and priorities. So, Jason, mic's on you, man.
All right, everybody can hear me okay? Great. If I could ask the panelists to please come on as I introduce what we're going to talk about. So AI assurance research and needs and priorities. So first of all, good morning and good day to everyone. We're here to lead off this. It's a very big panel. I've got 5 speakers, and a lot of great comments to share. Ask that you please be clear and concise and explainable with your answers to this. And so for the first 2 questions, what I'm going to ask you to do is to please introduce yourself, your body of work and your expertise. And the questions that I'd like you to answer, the first question is please name your top 1, because we're going to get through 5 of them. So your top 1 challenge that in AIA that research can help solve or predicate a solution to in the future. And with that first question, then the second one is what resources do you have today to perform that? And more importantly, what resources are you missing? So those are the 2 questions. All right. And I'm going to ask for Dr. Fan, if you could please get started with our panel on that answer.
Yeah, sure. Hi, everyone. This is Chu. I'm assistant professor at MIT in the Aeronautics and Astronautics department, as well as the Research Lab for Information and Decision Systems. So I work on safe autonomous systems. I work with my group of students and postdoc here to develop methods and tools for the design, analysis, and verification testing of autonomous systems. We look at a very broad range of applications in both aerospace and robotics. So from my perspective, like the number 1 priority in AI assurance would be the scalability issue, because like I'm in the academia unit, we develop a lot of fundamental methods, mathematics for solving this very hard problems in verification and certification testing. And if we look at this, from the theoretical perspective, a verification or assurance problem itself is a hard problem or computationally difficult problem. So anything we want to develop will face the curse of dimensionality. So if we look at the systems we were able to handle in the past and look at the scale of the AI systems and algorithms of today, they're not really comparable. So the size of the AI system these days has gone way beyond the capability of any existing verification and certification technology. So I think, to me, the number 1 priority is to, instead of keep looking at what's the existing methods to address these new challenges, we need to develop new methods to address these new challenges. So that's like my answer to the first question. And the second question is what resources we have. So we are an academic unit, so we do have sponsored projects from the federal agencies to study the assurance problems in autonomous systems and in AI. And I personally have a few projects working with different government units. And I think that's really a useful resource for us to explore the problems here. And I think what we can get more, a couple of things. One is more like emphasis on the educational aspect, especially for not only for the students, but for the policymakers, the stakeholders, to so we're on the same page to understand what the challenges are and where the technologies are. And as within the academic unit, we're also really in need of a lot of computational resources to keep the pace of today's AI algorithms, and especially developing assurance methods for them. So I hope that's can start the conversation from here.
Yes, absolutely. And thanks for putting it out right there, that big chasm of a problem in between scale, right? And scale is like the thing that we hear the most about. So Dr. Koopman, I'd like to turn it over to you for the same answers, or not the same answer, same question. I apologize.
I got you. Hi, everyone. I'm Phil Koopman. I'm a professor at Carnegie Mellon University. I've been working on self-driving car safety for more than 25 years, back to the Automated Highway System project back in the 90s. I think the biggest problem I see that's technical, and it's not clear to me the technical problem is really the problem that matters, to be clear, but we can get to that later. The biggest technical problem is what I call the heavy tail problem. This is technology based on statistics, and statistics are absolutely terrible at 99.999999 kind of things, right? And the thing is, on a good day, a good AI system will give you 98%, 99%. And for many things, that's amazing. It's really amazing technology. But at 100 million miles between fatalities, 1 million miles without a fatality doesn't even get you in the game. 99 more million to go, and then you're only at 70% confidence or whatever it is, right? So the machine learning type techniques are fundamentally not a great match for things where the events you care about are way out at 10 to the minus 7, 10 to the minus 8, 10 to the minus 9 per hour, a lot of seconds in an hour, okay? So there's a fundamental technology mismatch, and how that shows up is no practicable amount of testing can reveal all the issues you're going to have to deal with on the road. And how do you deal with that? And so assessment is tough because nobody has the complete list of all the things to check. And it's inherently not practicable to get that list. In terms of what I work on and my funding, well, I don't have any funding. I don't have any resources. The United States government has systematically for decades not invested at all in functional safety and related things. It's just not, we just don't do it. The UK does it, Europe does it. There's a whole Assured AI Institute in the UK that has its roots in safety engineering rather than AI. That's just not a thing in the US. And as a result, you see very few faculty in the US, very few, and the few are all retiring. I'm retiring in January, so I don't have a stake in this fight. This is not self-serving. I'm not saying give me money. I won't be here to get it, okay? They just don't invest. And so what you see is a lot of AI safety being AI stuff with a safety label slapped on, and there's value in much of that. But that's not going to solve the safety problem because the US doesn't invest in safety. Simple as that.
Thank you, Phil.
And with that, I'll move on. With that happy note, I'll move on to the next person.
All right, thank you so much. And it harkens to some of what we heard earlier in day one as well, and in the beginning of two. And Missy, I see that you've been able to join. Sorry that there was some technical difficulties. Thank you so much for being able to join us today. If you do recall, just a quick introduction of yourself, and then the first question I'd like to ask you is, what is the #1 top challenge that you're seeing in AI research today, in the AI assurance research today, and then your top resources and what your needs might be related to continuing and furthering that work.
Thanks so much. So Missy Cummings, I am at George Mason University. It was a recent move from Duke University. Really inspired by the time I spent working with the Department of Transportation as an IPA, really kind of made me want to focus my efforts in DC because I feel like that this is the area that I can have the greatest impact. And, so many of people who are from DOT, we know each other, I don't hold back. And so you can rest easy, because on this call, I am going to not say anything controversial about anything to do with DOT because, I'm on your side and I appreciate the job that you have. But when it comes to AI assurance, the real culprits are academia. I'm just going to go ahead and say it. I have many friends in the formal methods community. You're all failing. That is one community that in theory says that they're doing all this AI assurance work, and what they're doing are playing toy problems and just trying to come up with elegant methods that make a good paper, but that don't actually solve anything. AI assurance in the form of formal methods, it just doesn't work. It doesn't work because the assumptions that have to be made to do linear temporal logic approaches, for example, please, I'm just tired of it. It will not generalize to actual complex systems. So the more that we insist that formal methods in the guise that it's under right now is going to work, the longer we're going to take to get to a solution. Probably several times a month now that I'm no longer working for the government, I get contacted by the families of people who were in a Tesla mostly, but increasingly in other cars, that young people, old people, doesn't really matter, high influence people, no influence people, and their loved ones die because they don't understand how a system works. We know that the systems don't work. And DOT, especially NHTSA, has come on really strong lately to start doing investigations and trying to get companies to toe the line. But academia, look, I'm tired of sobbing people on the phone with me. We promise that we're making tech. That's true for self-driving, anything with neural nets, including large language models. Tech has basically co-opted academia to be their salesman and to do research only to make bright, shiny objects. And what academia is failing at is actually sitting back and saying, wait a minute, have I really done due diligence? Are my promises really true for safety critical systems? It is almost as if academia is doing a lot of 6.1 research, but trying to sell it as 6.9 mature research. And there's just no checks and balances inside academia to actually tell people, look, just because you made this bright, shiny thing and it worked on one Kaggle data set does not make it work in the real world where people's lives are on the line. So
true.
I wish that we were doing a better job. I don't have enough research.
Oh, Missy.
Safety. I do. I agree. I don't. I'm going to wrap it up. I agree with him 100%, but
Missy, we're starting to get a little bit of audio choppiness on you there. Maybe your cell phone can. Hello? Uh-oh.
Okay. All right. I'm just going to wrap it up there, and I'm going to try to move my phone closer to the window.
Okay.
There you go.
Thank you. And sorry about that, but and well said, I think, Missy, right? Really what we're trying to do here is lay out some problems, right? We heard from Choo Choo and Phil and Missy now, and so now I'm going to pivot over to Bob to start and ask Wafang that you please close out this part of this. So as we think about all of these new needs, right? And as this continues to develop, and a lot of them aren't new, but they're becoming a lot more noticeable by others, right? And so with that in mind, starting with you, Bob, how would you answer these two questions?
Hey, good day, everybody. Let's start with the intro, right? Bob Sheehan, I'm on Brian Cronin's team, and I'm the designated PE for this panel. So shout out there as well. So I'm with the ITS Joint Program Office. I currently lead our work in the National ITS Reference Architecture, as well as ITS standards, and also have been supporting and leading our development of work in AI for ITS. This started a few years ago, and there's all a history of where executive orders in the late teens and after. One of our core efforts within the office is to look at all technologies, new technologies, emerging technologies, and evaluate the potential for the transportation system. And we apply, hopefully, a reasonable process to look at the different application areas and use cases to identify what it would be. And so we would do the same thing for AI. This is I started probably in 2019, 2020, probably even earlier, maybe. And it continues to this day. I was thinking about this quite a bit since last week, preparing for the session, looking at two different avenues. The approaches we've been taking, it's almost constrained in two different areas. It's preparing for something. It's preparing for those what if scenarios, because our work is looking into the application areas, which really gets to the challenge. It's not just one challenge here, Jason. It's because I am looking at across the board, and it's the examples of what Brian was referring to in the overview. It's I'm not necessarily looking inside the vehicle. Other people are looking at the performance. I'm looking at the other applications within the ITS framework, accessibility for people focused on their needs, asset management, roadway construction, traveler tools, commercial vehicles, freight operations, emergency management, transit, the whole world of traffic systems management operations, to understand the potential, right? And I'm trying to break it down from an engineering perspective, looking, okay, where are the needs to sense the environment, to better understand the analytics and the reasoning, and then ultimately the last step in the process for communicating and taking action. And in each application for each user, it's a little bit different. And so The challenge is taking that framework and applying, breaking those discrete steps to understand the application of where, what things are considered safety critical, what things are, looking at how AI can be applied in those application areas to reveal the needs and the gaps. And so the policy guide rails, that's like the second track. It's like we're doing the how AI can be applied, and the other track, which is independent of us, is what are those guide rails for use, and so that we can be ready for. So applying like equity, bill of rights to other areas. We talk about safety, but I see safety as the impact on a number of things. Inequitable solution means you're impacted. And so that's really, so the challenge is there's a lot there, right? It's more than just one challenge, it's a bunch of things. And then the second thing is the kind of research, the kind of resources. One of the things that we need, and I'm focusing on now as I develop our work, is to address what was kind of said here is, what is the methodology for decision making? I want to do the right work. I want to do the right work at the right time. And so work on this now. We started working on the application of the risk management framework from NIST, but in the overarching methodology, this is a key part of it, the effort we're having right here. So I commend Fong and Taylor in the office, in your office, Jason, because it allows us to apply that approach. We've done some other things where we tried to look at a capability maturity model for AI, just for state and local and tribal entities, because they're the ultimate deployers. I'm looking on the infrastructure side. I'm looking on the state, the IOOs, and to make sure that the technology that we are looking at reviewing or researching, it can be deployed confidently, which really gets into the core of this session is how to define that confidence. And so the liability associated for a traffic engineer at a signal is different than a person who may be doing something that is less safety critical. So for me, the second question is really getting to that methodology for decision making.
Thank you so much, Bob. And as a previous city executive who joined the USDO team just recently for this reason, and for all the reasons that the panelists just named, it goes without saying that the biggest need is down at the local level. So to close us out, Wafang, on this session, on this piece, if you wouldn't mind, please take us home on your perspectives to these two questions.
So yeah, thanks, Jason. I have a very mixed background from industry to government, and still work a lot with academia. So first, I probably introduce my background. So I started this work, including the form method verification and safety from Toyota. So I have been working there for 4 years, and then I moved to Boeing for 7 years. So I have been working a lot on the automation, autonomy, safety research. So that experience helped me to understand better, the technologies and the challenges, not from just the industry, but also from academia. And you can imagine we do have a lot of challenges from industries for the safety of highly automated systems. And I found it's very hard to address that by just individual researchers or one company. So we need a lot more in coordination and collaboration. That's why I decided to join this new office, Highly Automated Safety Center of Excellence. It provides this very great opportunity to work with all the collaborators, all the stakeholders for all the autonomy technologies, platforms, and all the stuff. So from my perspective, we try to make this collaboration between academia and industry and the government. But the challenging thing is we all do the different things, right? On the government side, it's more related to policy regulations, and the researchers more on the research challenges, and the industry more on the engineering and also the operations. So we want to figure out how to build a good plan to collaborate with each other. as Phil mentioned, we have several challenges for the safety. And currently, our approach is really to learn from industry what are the safety challenges, and then work with academia to figure out some solutions. Of course, we also need to work with industry. So based on this, for me, the biggest challenge is to build a good framework, safety framework, or currently we talk about AI assurance framework that can help to get everybody on board to work together to address the major challenge of safety for highly automated systems.
Thank you so much, Huafeng. And I think well said how holistic the world is. It's a complex system of systems. And so therefore we need as much commonality in our approaches as possible, because the different applications of AI, to what Bob was saying earlier, they're going to be all over the place, right? So I think we have an opportunity right now. If I could ask Manaski to come on, I think we have a Menti that we'd like to ask the audience to please participate in.
Yes, so thank you, Jason. So on to the second poll question of the day. So please use your devices. And all right, so the second question is, to what extent is research on AI assurance keeping pace with the development of emerging AI technologies? And so I've opened the responses, and I'm going to set a timer from a minute.
And while that minute's going on and you guys are answering those questions, I'm going to fill this time with some talk around, what some of these follow-on general questions are that the group had in advance for us to look at here. And so, as we kind of lay out the next steps to this, I want everyone to kind of think about what is that current situation in our national AI assurance strategy, which is a budding and brand new strategy in a lot of ways, and it's picking up in midstream, right, of a lot of activity that's been happening as we've been talking about. I'm going to ask you guys some pretty pointed questions. Again, this is a pretty provocative panel. I mean, we want to get some energies going for day two. And so, I wanted to ask, related to the research piece, some questions around strategies of research. So I want us to use this to really think about what are our strategies that we need to be thinking about as we look towards our next research needs in our community and such. So
yeah, so we did receive
Meenakshi.
some responses. Yeah, we received some responses, and I think so far we have 74. I still, have the poll open in case folks want to respond to it. But it looks like most of you said only a small extent that, the AI assurance research is keeping pace with the development of AI technologies. So which is not a great sign.
And maybe to be expected a little bit for our country, right, too, as we look around the room, we're surrounded by professionals in our own space. So again, we're talking about things that are the big elephant in the room. So that's a good thing to do right now. So with that next question, I'm going to start this off with Dr. Yu. Huafeng, if you could please, what are your overall strategies as you see as a national AI assurance model begins to roll out into the United States?
Yeah, I have been looking for this for a long time. I'm waiting for a national strategy for AI assurance. And of course, we have the new executive order on safe, secure, and trustworthy development and use of AI. This is a very, very good start. And it provides a lot of very good principles we want to follow. And at the same time, we also consider several other organizations like DoD and NASA. For example, DoD has a data analytics and AI adoption strategy, and NASA has its autonomy verification and validation roadmap. And recently, FAA also starts a new effort on the AI roadmap. It's currently under review, internal review. It should be published very soon by our colleague Zhongfa. So we have a lot of strategies to follow, but for transportation, you can imagine, finally we will need to build our own strategy, right? So we will need to work with academia and the industry and also other government agencies. We work together to develop this future strategy.
Understood. Thank you. Very, very succinct. Missy, I'd like to ask you next. What do you think is the strategies that we need to be thinking about as we roll out something nationally, to add on to what Wafeng mentioned?
I think that we need to make sure that we have a broad enough definition of what should fit within AI assurance. I spend a lot of my time looking at AI testing and certification, which is, I think, within the assurance wheelhouse, although maybe not everyone agrees with me. And this issue of looking at some of the fundamental issues of how we assess goodness of outcomes, I think is critical, because if you're not making the right measurements, then are we actually, everything that we build on top of that in terms of assurance, it's critical then that we make sure that what we're measuring is in fact good enough. And for example, I'm coming out with a paper soon that really kind of questions, for computer vision, we like to do this mean accuracy precision measurement, which says, like, if an algorithm can recognize a fire truck 85% of the time, in academia we consider this good. Well, no wonder we have cars hitting fire trucks all the time. 85% is, as you heard Phil say, it's not even close to being the kinds of low reliability or low issues, low detection issues, that would be acceptable for any kind of safety critical system. And so I think that we need to make sure that we're bringing all the people, the right people to the table, to make sure that we're taking a 360-degree view of what it means to assure AI. Of course, I'm going to shout out, we just started a new responsible AI program at Mason, which includes testing, certification. We also consider the ethics, but also things like formal methods. And, so I think that we need to be clear that AI assurance is not just one thing, but I think maybe that would be a good next workshop, is to define what do we think should fall under the umbrella of assurance.
Love that. And the whole thing about who's not here. I think that's a theme that if the rest of my colleagues could pay attention to that as we continue today, I think that'll be a great summation as we continue throughout the day's activities. So Dr. Fan, if I could ask for you to please, given your large experience in aviation, from an aviation perspective, how do you see this? How do you see aviation fitting into what you've heard today?
Yeah, there are a couple of things definitely echo on what Dr. Yu and what Missy has said. And a couple of things. First of all, in terms of the strategy, I want to add one thing, not only limited to aviation. I feel like something that is needed is to clearly understand the scope of the problem or the game that each player can play here. I can give one concrete example, like, for example, in the AI or larger language model domain, people are talking about some level of assurance. They have this concept called constitutional AI. Basically, you have to make a constitution of what the AI system can do and cannot do. And if you look at who is leading this research and the deployment of constitutional AI, it's all industry. It was initially developed, talked by DeepMind, and then Anthropic's one of the second biggest large language model company. They're doing all this, and And the reason is because the scale of like this type of concept is way beyond what we can handle within like an academic unit. And for example, like each training of the large language model, if you want to embed anything, you have to, do this in a training. Each training now is costing, I don't know, I heard numbers may not be correct, but definitely billion levels of dollars just for each round of training. And then that's not for me, I'm very curious about like what each player is like, for example, researchers in academia or government, what they can do here if we just let industry to completely lead this game, then there will be a lot of consequences that it's hard to imagine. But at the same time, we actually really do not have that resource or capability to do anything there. Coming back to aviation, I feel the special part of aviation is like really the high safety standard in aviation is way higher than a lot of the domains like in social media or something similar to that. It's way higher than that. And then at the same time, aviation is also very expensive. It takes a lot of money and time to develop any system in aviation. So as a consequence, I feel like the decision makers in aviation, they are very reluctant to any changes. If a system works, they would rather keep it work for as long as possible. Like in aviation, you can still see things being developed 30, 50 years ago, and they're still working, and they will just spend their budget on maintaining it than making any changes to the structure or architecture of the system. So the adoption of AI, anything related to AI, will be very slow and difficult in the aviation industry. I personally feel that we really need a very clear cost-benefit analysis of what kind of problems that AI can help address. What is the cost of it? What's the role of each player that can play here? And then together, like work collaboratively to figure out the best way to make the technology advancement kind of also have impact in aviation.
Yes, very insightful. And it kind of leads me right into my question. Same question to you, Phil, but a little different because you're going to get to kind of take a little bit of what's going on here. So I'm going to, what Missy mentioned, that it reminded me of your talk yesterday. And so we're at this juxtaposition, right, of how do we bring together all these different activities, a lot of which started before we got started with AI assurance. And what, from your perspective, given your experiences, would you see as the strategy on how we unify this, right? How do we begin to unify an AI assurance model where we get everybody kind of on the same bus related to AI assurance?
I appreciate that question because I wanted to answer the previous one, but now I can do both. I think we are not broad enough in who we consider to be everyone. So if you were to ask me, I mean, what is something that's probably going to work to help with self-driving car safety and autonomous vehicle safety? My answer goes like this. The first is you have to realize this is a socio-technical problem. So when people say we're here to talk about the technology, you've already ensured your failure because it's a socio-technical problem. And I'm not broad enough to know everything about everything, and I doubt few, if any, people on this meeting who are, which means teaming, you have to work with other folks, which is why I now have law journal papers that I co-authored with a law professor. Okay, I never thought that would happen, but here I am. And so you need to do that. The other thing is technology is going to fail if the public loses confidence. And so if you don't have robust safety guardrails in on day one, the technology, the people pushing too hard for the technology will basically push us into another AI winter. I haven't heard that one making the rounds in a few months, but it will make the rounds again. If they're incentivized to take chances, but if they mess up, the whole industry suffers. So how do you do this? Well, a way that for sure isn't perfect, but might have a way of working is step one is you get some tort liability reform in there to make sure companies are accountable for the harm they do. That's not a technical thing, that's a purely legal thing. But I have a proposal with this law professor to do that with cars, to make sure that manufacturers can't lobby their way out of accountability, which so far they've done. There are state laws that make them the last people on the list who's going to do anything for accountability. So you make sure the tort liability is there. The aircraft industry, I'm not so worried about, but the other transportation industries have a lot of issues here. Once that's in place, that buys you some time to actually require safety standards, which DOT has a proposal. It's gathering dust to say, just follow your own industry safety standards. We're not gonna tell you what to do. We're just gonna say you have to self-certify you actually followed your own relevant standards, and if there's a problem, we'll check your homework later. So it's not even external oversight. It's just make the promise so that you incur some liability if you didn't do it. And part of that is the safety case argument. Tell us what you think safe means. Any answer is okay. Tell us why you think you're safe. Any answer is okay. But you have to go on the record, and we're going to grade your homework later when you make a mistake. That's also going to put pressure on them to do the right thing without, stifling innovation. Nothing I said stifles innovation. It stifles irresponsible innovation, but I don't think that's necessarily a problem. Okay, and then finally, over time, there will be more process and specific technology-centric standards. That's a 10 or 20-year play, and you can't wait and have the industry kill itself by deploying things that were pushed to market too soon. You're never going to have an industry if that happens. But that's a plan for putting guardrails out in incremental steps that gives the industry maximum flexibility, but holds them accountable for their choices.
Thank you, Phil. Thank you so much. And Bob, your earlier comments at the beginning of the panel around just the overall complexities of safety in transportation and how AI could be used, right? I mean, it goes well beyond some of the unique specific modal characteristics that we've talked around just now today, but it really gets into, how do we do things that are still age-old problems that still have gaps, to Missy's 85% point, that we're still trying to, work that 80-20 rule and push into more and more pedestrian safety and more vulnerable road user safety in other areas, these complete streets projects that you talk about, and so always so supportive of. As you look towards, the work of the ITS JPO, and being, and I'll sprinkle a flavor of that over that to something that Chuchu said earlier. If you're in a safety culture, if you're in a mission safety cultural agency, then there is that little bit of stretch that needs to happen in order to really get beyond some of the status quo. Can you share a little bit about what you and Brian have been working on at JPO and how that plays into this national AI strategy?
Yeah, thinking about this and thinking about the question and then thinking about the answers that were just provided, caused me to continue to kind of reframe what is coming into this with. And framing 80-20 is interesting because even some of the work we did years ago looked at accessibility and it went in a general stat. So don't hold me to this, please, but it's approximate. And for this conversation, it's precise enough. At any point in time, there are about 20% of the population in the U.S. has some mobility limiting disability, a number of different ways. And so it's 20% has some difficulty in navigating the transportation environment. That's just one area, and that ranges over time. And we are all going to move into a point where we have some limitations, which technology can be a solution in addressing that. And we've already done some research and applications in those areas. And so when you look at the full spectrum of things, and I was really leaning on the one of the first comments was what are the performance requirements for these applications? And it closed with define safety. We've done a lot of work over many years is moving from nominal safety driven approaches to substantive approaches, and the highway safety manual contributing to the safety, safe systems approach, getting to a better approach and for analysis and decision making for those solutions. So thinking of all those things and applying to what we're doing, it goes back to the challenge and why part of my effort and our effort is actually leaning on this type of effort, because this wasn't part of our overall approach. We were framing out a problem, but we did, meaning working with your office, Hafong Taylor, and I laughed because the way you framed it made me laugh, because one of your colleagues, I think he's on here, a dear friend, Steve Sill, used to laugh because I'm the PE, I'm the civil engineer. And so he'd laugh because I built targets and he was, more of a mechanical, and that was kind of a funny joke to me. But I represent that implementer's perspective. A civil engineer, a PE, I build these things and I support the development of these things, okay, across the board. Because of that, we also looked at, I think, all of our research and recognizing there's so many different challenges that we're faced with deploying in these different applications. We're looking at bias challenge, dealing with bias, the technology and supporting technology needed for implementers. We talked about the perception of stakeholders. We talked about having to deal with workforce development and dealing with ethical and ethics, equity, understand the privacy implications, security, a bunch of different things. So what we realized, we need to take a multi-pronged approach. It's not just here's one thing to solve the problem. So we're trying to make a better connection between the research and the topics discussed today as it applies to applied research. Like I think I'm more at the tail end. I'm at the we're ready to implement this, do it right, but I can't do that without a better connection to research, especially in areas that can jump a level of technology readiness very quickly. And sometimes if it jumps too quickly, agencies aren't ready to implement. And so we need to, so it gets to kind of like what we're doing and where our role is. We're trying to, I think that's where the role is addressing the assurance, addressing the risk, and I'm providing, use the word guard, or for your Pennsylvania, guide rails to help, develop on what needs to be, what can be safely implemented confidently, gets into liability, gets into all these things by the different users. So I'll summarize that with a multi-pronged approach, connecting these two together. That's really the key part.
Thank you, and it kind of brings into my last general question for everyone on this, which is, Bob, you point out some unique things around, really what's happening at the municipal level. And so just to share a little bit, I got to sprinkle a little bit of my own experience in here. At my level, before I joined in my previous job, whenever we would go to implement a new thing in the community, usually when we were doing that, and as we began in the early days, we would go and do it and maybe not plan as much and not get the results that we'd see. And so we started planning a lot more. And every time we do that, there's two things that would always come up related to it. And it was around a keyword that you used, bias, and more importantly, equity. And the biases that are built into all the parts of the transportation institution today that the communities are addressing, kind of as we go, as we implement these new elements within our built environments, as we build out more complete streets, as we look towards Vision Zero programs and how they work both that intersection and the middle mile, right, which is the newest thing that's being discovered in a way, but it's been around, the data's been around for a while. When we think about who we need to collaborate with, from the two perspectives I'd like for us to consider for the entire group. One, from an equity perspective, all right, how do we begin removing these biases and these other artifacts so that we can drive forward to a more equitable and more accessible transportation system? And number two, as part of that comment, what does that mean for the workforce? Because we've yet to touch on workforce, and I want to make sure that we touch on workforce in this panel before we get to the next Menti. So with that, Missy, would you please kick us off with that?
Oh yeah, I could talk about this all day long. I'm just going to briefly touch on the equity piece, which I think when it comes to artificial intelligence, to me, the big issue that we need to think about in terms of AI and transportation and equity is what is happening in what it takes to build the infrastructure of AI, specifically the labeling of data. Most people sort of say, yes, I recognize that we have to have a lot of data, but it's just a new modern form of slavery. in other countries around the world that were harnessing warehouses of people just to do data labeling for all kinds of applications of neural net. So I think that deserves more discussion. In terms of workforce development, I moved to a university so I could start a whole new education program in response that really puts AI as a common set of skills that I think everyone should have. I don't think that you should have to go to MIT or Carnegie Mellon and get a degree in computer science to be able to talk intelligently about AI. The University of Florida is now, I think, making, I heard they hired 102 professors so that everyone can graduate from their university, not as experts in AI, but that are just basically literate in AI. And so I think that, we're trying to do that at Mason. We have a new both online and in-person version of a responsible AI certificate so that people can get credentials. But I do think it requires a shift in people's understanding that AI is just a tool in a toolbox, and you need a set of skills to learn how to evaluate whether that is the right tool to use, and oftentimes it's not.
Thank you, Missy. Thank you for that very important comment. Phil, same question. Equity and workforce.
Okay, for equity, I'm going to come at it a little different way, but it gets there, I promise. I think a lot of what I see is really fuzzy thinking about what you mean by safe. When you get, if you get 6 engineers, or sorry, 6 people in a room and ask them what safe means, you get 6 answers. If they're engineers, you get like 10, okay? And the thing that people miss is all of them matter. There is no single right answer for safety. All of them matter. We're back to socio-technical problem. And so if you really want to understand safety, you have to figure out who the stakeholders are and hear from all of them, and the equity stuff shakes out from that. If you're looking at funding research, I would really urge research funders to ask for really precise mapping, not just, well, what does it mean by safe? Say, no. Here's an application of a real world system. What contribution is your technique going to make to actual safety? And of course, it's not going to solve all of it, but people claim, well, it'll make everything safe. And at the risk of picking on the formal methods, folks, they do something that has value. But if they claim it's going to solve safety problems, no, there's still, what properties do you ask them to prove? And what do they do about the assumptions? And what do they do about the things that have uncertainty? And if they don't know how to deal with uncertainty, there's a bunch of questions. And I'm not saying everyone has to deal with everything. I'm saying you have to be intellectually honest about exactly how you're connecting to safety. And my experience has been, unless you force people to be very explicit about arguing from the safety goal all the way back to it, that they overstate their claims. And really smart, well-intended people, if you're working through an exercise, no, I'm going to hold your feet to the fire. Exactly what do you mean? They find out that they're contributing about 1/10 or 100th what they thought. And it wasn't that they were intentionally being dishonest, it's just they'd never really thought it through. So I think that kind of process will help us understand the potential research contributions from it. And we're going back to, well, all the stakeholders involved there. From a workforce point of view, partly we undereducate in safety. Safety engineering, it's been around for decades. Other countries have made a 50-year investment in that, and the US has not. There's anecdotal stories I saw in the chat, and I really appreciate the sponsors who've helped me. But there's a reason I have to go on a plane to Europe it used to be the 3 other professors out of 100 who were from the US. Actually, I was the only professor sometimes because the other guys worked for NASA or FAA. There was, 3 out of 100 people did safety in Europe because we didn't have the funding. So if you want to do this for workforce development, we have to start with getting serious about taking safety engineering and system safety as a legitimate academic topic in the US. I know that sounds dramatic, but that's basically where we are.
Yeah, I think it showcases, as I have not done a whole lot of work in aviation, and in joining this team, I've been able to get a big exposure to aviation thanks to Wafang and others in the group. And I look to Chu Chu, everything that Phil said, it just, safety continuum started resonating in my head. And when I think of that, I think of, the FAA's sort of approach to safety continuum and that. And for you, from that perspective, then what would you see as how to answer both that equity and workforce problem?
Yeah, I hear a lot of what Professor Koopman said. I do feel like within the we focus too much on the technological aspect of safety, but there are just so many different aspects. Like, for example, a very simple example would be the psychological safety that we almost don't mention, but it's play a very big role in safety. And really, we need to, if we want to have like AI to be engaged in our daily life, we need to solve this much bigger societal problem to enable some collaboration between like social scientists, the psychologists, engineers, the lawmakers, to be on the same page when we think about what are the standards and metrics and expectations for AI assurance. And another thing I think related to both equity and what the workforce could help is to bring like people together to share information. For example, if we want to understand what causes failures in a lot of either the self-driving car or some of the AI algorithms in these cars running around on the road, it's all like industry has ton of data. All these companies, they collect, I would imagine, like ton of data, and especially the failure data that they have. But I don't think they are willing to share any information with researchers or like not stakeholders of their companies. And maybe in a lot of cases, they want to hide as much as possible. Without even accessing to those information, those data, what would you expect the academic people to solve? So I do definitely agree that like the forum method community and many other communities, they oversell what they can do. But I feel like there are two issues that kind of cause this overselling problem. One is if they don't oversell, they don't get any resources. That's kind of like becoming a culture these days. Like you write a proposal to some agency, you have to start with like solving this very big problem. And what you ended up getting is like 100K and for supporting a student. How do you imagine you solve any problem that scale with this little support? So then like there's like, but if you don't oversell, you don't even get that 100K. Then there's kind of getting into a pretty bad negative like loop there. So people are over promising what they can do. At the same time, I believe like the students and the researchers, professors, they want to solve real world problems, but they don't have access to what the real world problem is. We see like if you look at a lot of the presentations, they start with like a Tesla accident, but really we have no knowledge about what has caused that accident within universities. And even if we want to analyze anything, it's just nothing that we can start with. Then what we can do is to create some toy examples. If you look at the tens of thousands of machine learning papers at the top machine learning conferences, they pretty much all look at toy examples. They don't have access. And if anything has like a real world impact, they either will be proprietary information that cannot be published, or they will want to protect it to maybe do some business on top of it instead of sharing it as like a research advancement. I don't know the solution here, but I feel like the workforce and the government can play a role here to collect useful publishable information and define clearly the issues, the assumptions, the scope of the problem, so people can start to look at those instead of just to stay within the toy example domain to solve this. Sometimes it's like I feel like they don't have much choices than solving this example.
Yeah, well, I think you pointed out something that we all feel, right? But we need to drive towards a more incremental build out, right? And to kind of some of the comments that Bob made earlier, how do we optimize the things that we can optimize today with AI, and assure that those things are working before we look at this big bang thing, because there are the people that we rely on to actually deliver these solutions and keep things sort of, at a calm state are the cities, right? And so how also do we then transfer that to them so they can force multiply what we've learned, right? And so with that, then I'd like to really ask Wafang to take us home on this question. From your national perspective of looking at this entire AI assurance program, what are your considerations as you look towards equity in workforce?
Yeah, I totally agree with all the comments from Missy, Phil, and Chu. I always feel very confusing when I talk about equity because we don't have any metrics, good enough metrics to measure if it is good or not. So if we consider the different time, geographical areas, race, or some other aspects, we don't really have a very good measure for that. And it's very hard for us, scientists or engineers, to address this problem if we don't have that metrics. And regarding the workforce, I know there are a lot of challenges. So I just talk about the DOT, our current effort. So you can see that we set up this series of workshops to give our DOT employees good opportunities to learn from our side, the researchers, and the next time from industry. So that will be the first step. We want to have a big picture of the technologies and what academic and industry are caring about at this moment. And then we can have some follow-up actions. And beyond that, we also want to set up the community of interest for AI assurance within DOT or potentially with other external collaborators. So we will set up a series of tech talks, invite our faculty, industry researchers or engineers to come to DOT, give the talk, have a deep dive conversation with our DOT employees. So progressively, we want our DOT colleagues to understand the current status of the technology and probably also all the other different concerns.
Thank you so much, Wafang. Thank you for taking us home on that one. I think we're ready for another poll to the audience. Is that right, Meenakshi? Are we there?
Yeah,
Awesome.
That's right. Thank you, Jason. All right, so moving on to the next poll question. So this is a statement. There is sufficient translation of AI assurance research findings into practical tools and methodologies for developers and practitioners. So for this, again, we'll take about a minute. So please indicate if you agree with this statement.
And as they're answering that, panelists, to close us out today, I'll be asking you one question out of the questions, the personal questions that we asked, the individual questions, and asking for a short brief remark on those before we do a last Menti poll. And then at that point, we'll get close to a break and give everybody a break.
All right, let's look at the responses. Oh, yes, so majority of you disagree, strongly disagree that there is, that there are practical tools that based on those research findings. So I think I will turn on the responses. So if folks want to continue to respond to this, can. And then I think I will turn it back to, is it Jason or Perfect?
Back to me.
Okay.
Thank you. So that's really interesting, right? But I think it showcases what we've kind of been teasing around in this panel, right? Is that there's a lot of work that needs to be really collected, concisely with a level of clarity and explainability. And then somehow we need to figure out how to translate that, right, to the people who need it the most today. And so love the fact that that is where we are, and we are seeing that across our audience as well. It gives us good work for the future, as they say. So going into the individual questions, Missy, I'm going to pick on you first. Not to pick on you, but I'm really interested in one particular question for you, and it's around the human automation component and AI assurance. Can you explain how or is AI assurance really considered or accommodated in a human automation type of system?
So I think the question really speaks to, I think it's the other way around. I think if you were to ask human factors people,
yes.
you would say, should AI assurance be part of that? Everyone who does human factors would say absolutely, and no one ever listens to us. That's a topic, that's a discussion for another day. I think, having been on the other side too, looking at people both in the industry and in the government, how much is the human automation interaction issue taken into account when, for example, working at overall AI assurance? It's really uneven. The Boeing 737 MAX is a good example that it wasn't taken into account by a company who otherwise I would have thought does a great job. Tesla, in a recent deposition, or several depositions, has made it clear that they don't believe in human factors at all, so they don't take it into account at all. OpenAI had an AI safety team, and then evoking an Elon Musk move, fired them all, right? So I do think that when financial pressures hit a company, that is the first element that they get rid of, the human automation interaction, especially the assurance component. This is why I like to plead to this group of people. This is why it's super important that regulatory agencies exist and make sure that they put the pressure on that is further. More AUC kinds of system means more and more AI assurance that we're going to need.
Well said. Thank you so much. Chuchu, from your perspective and thinking about things like human factors, but then bringing it into the fold of design assurance, could you explain a little bit about your work in design assurance and how that might correlate to what we're talking about?
Yeah, definitely. So I'll be a little bit specific here. I'm not saying this is the general solution to design assurance, but our research has looked at a lot of how to embed the assurance and certificates into the machine learning process. So especially when there's a conflict between the performance and the safety. So in a lot of the cases, the current machine learning community, they only look at performance. And even if they consider safety, they kind of like penalize the unsafe cases, but without any guarantees. And what a lot of our research is looking at, kind of building this assurance and certificates into the training process. So the system will have to produce something that can prove themselves about the safety property they want to satisfy. At the same time, then on top of it, they can achieve as much good performance as they can. So that's one big line of the research we're doing. And the other line would be understanding when a system is more likely to fail, because I believe verification itself is an NP hard problem, or harder in the sense that it's just for this big scale system, there's just no hope as of today within the resources we have to give the level of assurance that we want. But from the other perspective, we can always understand why this failure happened, what has caused the failure, what we can learn from these failures, how to test our system more smartly for future development of the system. So those are some of the directions we're working on to help with design assurance for autonomous systems.
Excellent. Excellent. And it kind of leads me into Phil, from that perspective of resources, right? I mean, I think I've heard that throughout this panel today is the massive amount of resources that we need to do all this work that we need to do. So from your perspective, on those questions, I'm really kind of focused in on that, going back to, but really just your opinion on the challenge of resourcing. How would you see a way for us to begin really accommodating all the resources? Are they there and they're just not connected, or is there really big gaps?
You mean with the researchers getting access to the information?
Yes.
Yes, that's
yes.
hopeless. It's just not going to happen. So let me answer a different question that you had for me, which is about standards.
Okay.
This has been a problem as long as I'm a professor. You have to establish industry collaboration. It's very hard to do. It's hopeless. But let me answer the standards questions. You had a question about, are the standards we have good enough? And I want to sort of build on what we've heard. We keep hearing these companies saying, don't let the perfect be the enemy of the good. Let us deploy our image shower technology. But then when you say, the industry wrote safety standards that have been out for, UL 4600 is on its 3rd edition, all right? All right, so these industry consensus safety standards have been out there. What did they say? Oh, it's not perfect, so we don't have to do it at all. Well, don't let the good be the enemy. I'm sorry, don't let the perfect be the enemy of the good on standards. Conform to the good standards and work to improve them in parallel with the technology maturing. If you're spending tens of billions of dollars on the technology and can't find money for safety standards, it means you don't want to do them. It doesn't mean that they don't apply. It doesn't mean it can't be done. They're not impeding innovation. The industry just doesn't want to do it.
Yeah, and I see that. I feel it too as an old practitioner in the ITS industry. When things like systems engineering and Rule 940 came out, there was a lot of talk around, oh, this is too much. This is not the right way to do this. You had different voices out there trying to pull that down in some kind of way. And so, Bob, I mean, I'm going back to our long-term careers, my friend, in ITS. And, to that piece, I think this particular question might be just a good one for you to follow on off after Phil, and then add in any last-minute things you'd like to add in on it.
Yeah, I was really happy that you mentioned standards, because it's a crossover between the focus areas that I'm addressing, and then diving into that area for our AI work. I think that's a key part. And so I've been thinking, for those last couple of things, I think about to address that, and I'm still reminded of a comment that Brian included in the intro when he mentioned kind of the perception, kind of summary from yesterday a bit. A stakeholder, the perception, either the need for like workforce development because of two things: either one, overestimating or too much confidence in what AI can do, or skepticism. And what I thought, and this has just happened recently, we were at a workshop with traffic with state DOTs looking at approaches for improving short-term predictions for traffic operations. So, and I feel like I apologize. I feel like I'm being the wet blanket and not addressing the importance of safety. And that's not my intent here. It's just looking at the full complement of things. And that's actually one of the challenges. We have competing objectives. And so at some point you're recognizing, I want one, I want the other. So this case is just an example of perception, where we were working with folks in Florida, and I was working with the Office of Operations, and they were utilizing a multi-resolution model, microscopic and a macroscopic model and meso together. And they were utilizing or starting to pull in an AI model and comparing it to the performance of their other model. And he used some terms such as labor intensive and then explainability in this conversation. So we came back and followed up on that. And the response surprised me, because 4 years ago, he wanted to do work and the response was, don't do it. Too much risk. Now he doesn't want to do work because of risk, and he's getting the response, do it, by his local city, because they didn't have a complete understanding of the consequences of the work being done. So it was a little bit of shift, and I was a little bit surprised by that, right? And so, to me, it gets into the core of this effort is providing that support to address what the equity implications are, where the consequences are within this, and that gets to the performance requirements, and then it gets to standards. They have to cover a number of different things, and I think that's a critical part, and it's a critical part for a role that we can play and we should play. Because we look at what is our role in engaging the academic institutions, engaging the industry, and engaging the deployers, because ultimately different parts have different responsibilities. And if I see our job, I think, is to find those gaps and say we need to address that gap because it needs to be done, and no one's doing it, or it needs to be done and someone's doing it but they're not doing it right, along those lines. So I think the standards was a great way. Thank you for mentioning that. And then that's what I want to, I look forward to focusing on that with this effort.
Yeah, I appreciate that too, and I appreciate Phil saying, "No, I want to answer this one." So thank you, Phil, for helping take us home. And brilliant responses, Bob. It kind of makes me think about how this burgeoning community of practices is getting so much activity, and it's going to continue to grow. And so, Wafang, if you could please close us out on this, and then on how you see this happening from your perspective.
Yeah, this is a very new area. It's a part of the whole safety process, right? It's just a small piece. Even this small piece is still a net blocking point for the whole automation systems safety. That's why we want to set up these workshops and probably establish this new community of interest or practice in the near future, so that all of us can work together. And of course, we still try to figure out how to work together. Of course, from the DOT's perspective, we have funded programs, projects, but we are also looking for some other technical exchanges. And we can write papers together and educate our DOT employees, support our operating administrations, and also let all the stakeholders know the current progress and the potential solutions and the directions. So thank you, Jason, for the great panel. Really appreciate and really enjoyed all the conversations of the panelists.
Thank you, Wafang. I think we have one last poll for the scope of this panel. If we could bring that up. Thank you.
All right. Thank you, Jason. So this is again a statement. There is sufficient research on effective ways to educate and train the future workforce in AI assurance practices. So you again have a minute to respond. So please let us know if you agree with this statement.
Good question, and I know a lot of the team, the planning team behind this, we're also looking at these questions and thinking about what questions we're going to be asking in our next opportunity to convene. So I think it's a great application of how US DOT, Haas, and its partners are finding ways to lead and convene conversations like this. All right, what do we have?
Strongly disagree. So there's a whole lot of work cut out for the DOT.
So I think we know what we're going to be working on in the future.
Yeah.
Excellent. Okay. Well, we'll keep that open for a little bit longer. I would like to very much thank, and I think Missy may have dropped, but I would like to thank all the panelists individually. Thank you so much for your very well thought out responses. I know that this is, we took this conversation in a bit of a different fashion, but you responded extremely well. And I think we ended up with an incredible conversation for the community. So thank you very much. With that, I'll turn it back over to Taylor.
Thank you, everybody. We're going to be taking a break right now, and then we will be convening right at 1:15. Thank you.
All right, everybody, it's 1:15. I know it was a little short of a break than we originally anticipated, but following on from yesterday's very packed agenda, we just have a lot of content, and we have two more sessions to go in the afternoon. So we still have a lot more content to share. So we might as well just get started. I know people are going to start to filter back in from a little bit of a break. So as Huafeng mentioned, we have 4 thrusts within this workshop for these last 2 days. Well, we're going to do the third of those thrusts in this upcoming session. So it's the session is going to be on design time assurance, and we have 3 fantastic panelists. And so the first panelist that we have for this session is Dr. Karina Passarino, and I'll just hand it over to you, Karina, if you want to start. You're currently with Carnegie Mellon, is that right?
Thank you. Yes, actually, I'm a researcher at both Carnegie Mellon University with Scilab and also NASA Ames Research Center. So let me share my screen. Can you see my slides?
We can.
Okay, great. So I will start. So thank you so much for inviting me to this workshop that is very interesting. Today I will talk about SafeDNN, which is a project that we have at NASA Ames. And I should add that my background is informal verification and software testing. And in particular, we have been looking at deep neural networks, and I'll give you a short background that you probably know. So these are computing systems inspired by the biological neural networks in animal brains. They consist of neurons, which are organized in layers. Neurons can be active or not. The last layer contains decisions. They perform feature extraction and input transformations. They learn to do tasks by considering examples, and they can represent very complex and highly nonlinear relationships and can be used for different tasks, for example, for classification or regression. And on the right-hand side, I am showing a feed-forward neural networks. It takes inputs, it processes them through layers, and it gives outputs, and the parameters, the so-called weights and biases of the neural networks, are the ones that are learned through the training process. And neural networks have found immense popularity, and I list here some applications that are even before, LLMs. So pattern analysis, image classification, sentiment analysis, and so on. And of course, of interest to this audience is the use of DNNs as perception modules in autonomous cars. And of course, with this wide use of neural networks comes safety and security concerns. And I'm listing here some of these concerns that have been also the subject of our research. So one is the lack of robustness. And this basically means that small, often imperceptible changes to an input can lead to misclassifications. And this happens even for highly trained, highly accurate networks. And on the right-hand side, I show some classical examples. So the first example is a street sign that was modified by putting some physical patches on it, and now let's say a neural network will mistake it as a birdhouse. Another classic example is an image of a traffic light, which was modified by adding 11 white pixels. And now the modified image, which for a human still looks like a traffic light, would be mistaken for an oven. So you can imagine this can lead to problems if this is deployed, for example, in an autonomous car for perception. Another classical and well-studied concern is lack of explainability. So these neural networks are basically huge black boxes, and it is not well understood why a network gives a particular output. Another problem that has been actually the subject of our research, and I will talk more about it, is also the lack of formal specifications. So neural networks learn from examples, often without high-level specifications. An obvious challenge is scalability. So these neural networks are very large. They have highly interconnected structures. They often have huge input spaces that are, for example, high-resolution images or videos and so on. And these characteristics prevent thorough verification and testing. On the other hand, they are kind of fairly simple compared to traditional software. So they don't have loops, they don't have pointers or concurrency that typically are the target of the software analysis research. But traditional heuristics and coverage metrics are not adequate because of this super highly interconnected structure, and I'll talk more about that. And of course, another concern, which is the subject of the previous session yesterday, is what about the data? How can we know that we have enough data? What about if the data is unreliable? For instance, the labels might be wrong, the labels used in the training process, or the data can be poisoned on, or there is bias and so on. So in this project that is called SafeDNN, I'm working with my colleague Divya Gopinath, and we explore techniques and tools to ensure that deep neural networks, and by this I mean mostly we focus on the trained models, and also systems that use deep neural networks are safe, robust, and interpretable. And for me, being at spending my time at NASA, of course, we focus on autonomous systems. So I will start by highlighting some techniques and challenges that can be used for verification and testing of such systems. So of course, testing is widely used. There are many performance metrics that people use, accuracy, confusion matrices, and so on. But the problem is that it provides no guarantees. And as I already mentioned, that these neural networks have huge input spaces. There is also a need for manual effort. So in order to have the testing oracle, you need to check that the output matches the ground truth. And also there is a lack of adequacy coverage metrics. So when do we know that testing is enough? Another widely used technique, mainly at the system level, is simulation. Again, it provides no guarantees. We heard already that if there are rare events, it's hard to catch them both with testing or simulation. And also a problem is that it may not reflect the actual deployment setting, and it's also very expensive. Now formal verification is promising because it provides guarantees, assurance guarantees, and actually there are many tools that address neural network verification. And for example, we are working with Stanford, and they have some tools, Reluplex and Marabou, that are based on constraint solving. There are tools based on abstract interpretation and so on. But there are serious scalability challenges, but even more interesting, there is actually a lack of properties to verify, and I'll go back to that. And in our group, we have also looked at a particular form of formal verification, which is probabilistic verification, and there are tools for that, for example, Prism and Storm. And one can argue that probabilistic verification is more natural since anyway, there are the metrics used to evaluate performance of neural networks are naturally probabilistic, such as accuracy. These systems operate under uncertainty, which can be modeled probabilistically, and so on. So probabilistic models can be used also for controller synthesis, and anyway, but they provide only probabilistic guarantees, which can be enhanced with confidence intervals and so on. Another promising technique is runtime monitoring, and there will be a session on this later. This is attractive because it can enforce properties, but there are also serious challenges there. So one is the lack of ground truth. So a deployment, you don't have it. And also typically you only have partial or unreliable state information. So it's hard to define a runtime monitor without knowing what the system's state is. And there are also other techniques which enforce properties during training. There is a lot of literature on repair and so on that also fall under these techniques. So for DNN verification, I'll talk a little bit about the properties that people try to analyze. So I would say the majority of the literature on formal verification for neural networks focuses on just one particular problem, which is local robustness. And basically, this can be expressed by a simple analytical expression. On the right-hand side, I'd show what it means. So given a model F and an input X, local robustness guarantees that in a small ball around the input X, the output of the neural network is the same. And this is kind of simple to check. And as I said, the majority of tools focus on this problem. But there are some problems with this property. So first of all, it's local. It's only around one input. So it doesn't tell you anything about the global, what happens on other inputs for the neural network. So, and also it's somewhat artificial. It's unclear that this kind of bounded, non-bounded adversary is, realistic in practice. And also it's unclear how this kind of local robustness relates to system level properties. So once you deploy a neural network, we care about the behavior of the system as a whole, and this local robustness, I would say it's unclear how it contributes to the reasoning about the global behavior. We have done some work in that direction. So in order to go beyond local robustness, one can think of global robustness, where for example, this can be formulated that for all D, where D is some support set of a distribution, supposedly the training distribution of a neural network model, we would like that to check that F satisfies local robustness. Of course, the challenge here is that usually you don't have a mathematical representation of D, of the support of the distribution. So there are techniques that try to learn D and then do verification over it. And we have done some work, and others have done work as well. And more relevant would be to check robustness to real-world distribution shifts. For instance, one would want to check that an object detector is, robust with respect to blur, haze, or contrast perturbations applied to images. And some of these perturbations have analytical expressions and then can be checked similar to local robustness, and we have done work on that. But the problem is that most perturbations, for example, snow conditions, don't have analytical expressions. So you cannot check mathematically this kind of robustness. So we have studied this problem, and one solution is to, for example, train generative models to learn such perturbations, and then add the generative model to your vision model and check properties for this composition. Another kind of property that people try to check for neural networks are input-output properties. So for feed-forward neural networks, they process inputs and produce outputs. So it's natural to formulate properties in terms of preconditions on the inputs and postconditions on the output. And I give here an example from ACAS-XU, which is the airborne collision avoidance systems that was also partly implemented using neural networks. And here I list a property that the domain experts wrote. So it says if the intruder is distant and is significantly slower than the ownership, the score of a clear of conflict advisory will always be below a certain fixed threshold. And we can express this in terms of input constraints, where the inputs are, the features, input features to the neural network, and then express the desired output in terms of the score of the output layer. And we can check this with, for example, the ReLUplex tool from Stanford. Now, suppose that one would want to reason about input-output properties for a vision model. So consider here the popular MNIST data set, which contains handwritten digits, and suppose we have a classifier trained on it, and suppose developer wants to write a similar property, to the one that we had for ACAS-XU. So one such property could be that if the input has a curve, the output cannot be 1. And looking at the data set, probably this should hold. But the problem is that there is a semantic gap between curve and the inputs to the model. So we lack traceability between these kind of high-level semantically meaningful properties and the actual inputs to the neural networks. And we have done work to address this problem. So we have worked on concept representation analysis of neural networks and also leveraging emerging vision language models to try to link a vision model to under analysis to textual representation of high-level concepts. Another problem that we have looked at is the one of generalizability. And this is typically measured by computing the accuracy of a machine learning model on unseen data. Yeah, and this is the typical measure computed statistically, but as you expect, it's heavily impacted by test data. And this is not a problem of out of distribution data. So even if the data is in distribution, and it's not about a problem of rare events, but simply because it's computed statistically, it may be wrong. And we have done a study and developed a tool called QuantifyLM, which translates machine learning models to C code, which are closer to the deployed machine learning model. And then we use basically constraint solving and the technique called model counting to precisely compute the exact accuracy for small problems. And for instance, we apply this tool on a machine learning model trained on solving graph properties where the input graphs are finite, and we can compute precisely the exact accuracy over all the possible graphs up to a fixed number of nodes. And we found that the obtained results are quite different than the accuracy measured on a test set. So the conclusion of this is that statistical results give false impression of good generalizability, but it is hard to pinpoint the problem. And other properties that one can check for neural networks include, for example, fairness for decision-making networks, which can be formulated probabilistically and checked automatically. I'm not sure how much time do I have. Hello? I hope you can still hear me.
Yes, you.
Okay.
Yes. You've got about. Hold on, let me just bring up the.
Yeah, just please tell me if I should perhaps wrap up.
Yeah, you're about what, halfway through here?
Okay, perfect. So Basically, at Ames, so I've highlighted some of the problems with verification. So it's not just scalability, but it's a bit hard to define what to verify. And at NASA Ames, we have a project called Prophecy, which kind of turns the problem the other way around and tries to infer input-output properties for neural networks. And the key idea is to basically infer these likely properties, which can be seen as a kind of contracts, using data-driven techniques. I don't have time to give you details, but then we can actually prove them using a decision procedure for example, using Stanford's ReLUplex or Maravu. And basically what the idea is that you can see a neural network, some kind of a program, and the logic can be captured by the on-off activation patterns, and the pre could be seen as some kind of similar to the weakest precondition in natural when you reason about programs. And we have two kinds of properties. So the precondition can be expressed at the input layer or at some intermediate layer. And I'm showing on the right-hand side some examples of properties that we can infer automatically. So on the top figure, I'm showing an input property in terms of neuron activations, and a layer property, which is, so the input property goes from the input layer up to some layer in the network, while the layer property is specifically constrained to a layer in the network. And we have found many applications for these kind of properties. So
Karina,
one is, yes?
I'm sorry to interrupt. I misjudged. If it's possible to wrap it up in the next couple of minutes.
I will wrap it up. So basically, I will also, I just wanted to give one slide on testing. So basically, again, so testing complements formal analysis techniques, but DNNs have huge input spaces and also operate under unknown environment conditions. So this means that it's really hard to measure adequacy in black box testing. You really don't know when you did enough testing. While white box testing, which aims to measure structural coverage in traditional software testing, has the advantage that operates over a finite model, the software itself, or in our case, the deep neural network. So it has the promise that somehow we can measure adequacy of the model itself. But the problem is that because of these highly interconnected structures in neural networks, it's classical test coverage metrics are not adequate, because, for example, one input can cover all the possible branches or the majority of branches, which are really activations in neural networks. So people have looked at adapting structural coverage metrics for DNN-specific problems, and we have a tool that incorporates different coverage metrics that could be interesting maybe for this audience, and it includes from neuron coverage to a modified form of MCDC coverage. And I will just close by saying that currently we are working on concept representation analysis to solve that semantic gap. And also we have worked on closed loop system level analysis and runtime monitoring, where the key idea is to view perception as basically a state estimator, and then we use classical techniques that work with errors in estimations, and this could be the subject of another talk. Thank you.
Yeah, thank you, Karina. I know this is such a big and complex topic. It's really hard to bound this discussion, but unfortunately we do have to. Can we move on to the Q&A, or we'll just put some, we'll start the poll Haley, if you don't mind. And if others can continue to populate the chat with questions from this talk, that would be fantastic.
Great. Taylor, I did see your hand up. Did you want to say something?
No, accident.
Okay,
Good to go.
just checking. Okay, it's time for a poll. Same code, same rules apply. You can use the QR code on the screen, and Meenakshi will put the instructions in chat if you haven't seen them already. So again, we appreciate your candid feedback on these questions. Current AI design methodologies are sufficiently advanced to ensure the development of reliable and robust AI systems. So your opinion on this matter? I'm just going to do 30 seconds this time, but I'll keep the poll open after 30 seconds because I know we want to stay on time here. I see the numbers going up. Awesome. And again, I encourage everyone to respond, no matter your background. Whatever sector you're from, you can be a USDOT employee. All responses are very valuable to us. All right, I will make sure it stays open. Oops. Okay. So, looks like another skew towards the disagree side, as has been the case for a lot of our recent poll questions. So I will turn it back to you, Prasad.
Yes, thanks. And I just realized I didn't introduce myself. I'm getting so caught up in the content of everything that's been talked about today that I forgot to introduce myself. My name is Prasad Gupta, and I'm a colleague of Huafeng and everybody else here in the Highly Automated Safety Systems Center of Excellence, HAS. So with that, let me now shift to our second speaker for this panel, Dr. Michael Warren. Dr. Warren leads HRL's Operational Autonomy Center, which engages in R&D related to adversarial machine learning, test and evaluation of autonomous systems, formal methods, and other areas. He joined HRL, which he'll talk about that acronym. I think it's Howard Hughes Research Lab, in a number of projects related to assurance, autonomy, and machine learning. So with that, I'm going to hand it over to you, Dr. Warren, so you can talk about the boundaries of design time assurance for autonomous systems.
Thanks. So are you seeing my slides?
It's blank right now.
Okay, let me try sharing it again. Okay. All right, is it working now?
Yes, it is.
Okay, so thanks to the organizers for giving me a chance to speak at this exciting workshop. Lots of really interesting stuff. And I'd basically like to tell you a little bit about my experience in connection with the design time assurance for autonomous systems. So, but first, I wanted to actually give you a little background on HRL, because I'm sure that we're not as well known as NASA or Carnegie Mellon or other organizations that are represented here. So as was mentioned, HRL is the former Hughes Research Lab that was part of Howard Hughes's aircraft empire back in the day. It was the research lab of Hughes Aircraft, the main campus, which is shown in the nice photo you're seeing, is in Malibu, California, overlooking the Pacific Ocean and right next to Pepperdine University. And we now have a few other sites sprinkled around the sort of Malibu, LA area. HRL is a kind of interesting place for autonomy research, partly because we're co-owned by Boeing and General Motors. And they obviously have their own R&D labs. So a lot of what we take as being kind of our mission is preventing the owners from technology surprise, and that largely means working on lower TRL technologies, working more closely with university partners, and working also very closely with the government. So that's our mission and that's our background. This is sort of some of the, I guess, highlights of some of the work that's been done at HRL over the years. So a lot of early work on development of laser technology and more recently, ultra light, ultra strong materials research, things like that. One that I want to highlight on this slide, and my main reason for including it, is that you'll see there in 1987 a photo of actually some of the colleagues I had, and I think one of them is still around, when I first joined HRL, in front of a kind of camper van looking thing, which was actually a early autonomous vehicle as part of a DARPA program back then on off-road navigation, using, at that time, autonomy technologies. And so this kind of history that HRL has been actually really valuable for, positioning us in terms of both the opportunities in the autonomy space, but also really kind of grounding us in what are the hard challenges as we look at these kind of low TRL technologies being developed in academia and kind of pushing those further, which of those things are actually likely to be relevant to the kinds of autonomy challenges, in mobility, written broadly. So it's been a unique journey in terms of that perspective. So I now want to shift and tell you a little bit about my views on design time assurance, and I want to start first by talking about design and the idea of design time. And so to me, the question of design time assurance for autonomous systems really is a systems engineering problem. So it's not a problem of training a model and testing it. It's a problem of actually how do we assemble an entire system in a way that we can assure the behavior of that system. And that has a number of different components that feed into it. So one is obviously the requirements. So the thou shalt nots and the thou shalts of what we want the system to do, what its constraints in its operating condition are, and how those feed through the design process. And so actually identifying constraints and requirements for autonomous systems turns out to be actually a very challenging problem in some cases. And that's largely in comparison with more traditional engineered systems where the functionality is fairly well bounded. Here in the case of autonomous systems, a lot of the functionality that's being taken over by machine learning components is functionality that previously would have been wholly delegated to a human operator of the vehicle. And so now trying to constrain that behavior in an appropriate way becomes a much more challenging problem. And in addition to requirements, there's the question of architecture. So how do you actually architect the system? And here I have a very basic version of the typical robotics kind of architecture stack where you have sort of perception, state estimation, planning, and control. But how you actually break those pieces apart and dive into the details of each one of those boxes impacts in turn the assurance of the system. So things like how you're doing sensor fusion could affect the downstream assurance of the system. So for instance, I've heard it said sometimes that, oh, well, we don't have to worry about the robustness issues that might be caused by these kinds of local robustness issues that Karina was talking about because we're doing sensor fusion with the LiDAR point clouds. But if you look in the literature, what are people doing when they're doing sensor fusion of LiDAR point clouds and camera? A lot of times they're actually using the camera outputs to determine which parts of the point cloud to look at. And so therefore, if things are wrong on the camera side, they're going to be wrong on the point cloud side too. And figuring out how to actually fit those pieces together and architect those pieces in a way that can actually be assured is, I think, a huge part of the problem. Additionally, models, of course, we do have nice old-fashioned physics models of the systems that we're working with that, make sense for the control portion of the system. But now if we incorporate a neural network somewhere in the loop, how do we model that in our reasoning about assurance? Data is another huge piece, of course, which has been mentioned in the session on data assurance yesterday, as well as throughout. and the fact that machine learning components are themselves very critically dependent on the data that they're trained on, and therefore understanding what the function or the impact of that training data on not just that machine learning model, but all of the other pieces of the architecture that that model interacts with, that's very critical for assurance. And then finally, simulation plays a big role, contingency management. What do we do if something goes wrong? If we're thinking about using autonomous systems to actually get humans off the loop altogether in some cases, then how are we going to handle things when they go wrong and there's, maybe no one or fewer people to actually take over? And finally, one I want to highlight is actually failure and misuse. And here I've got an image from a pretty nice paper from a couple years ago on adversarial laser beam attacks on sign classification, and the fact that these systems are actually often much easier to fool, and sometimes to fool in very targeted ways, and often with actually a fairly minimal amount of effort. And that failure of robustness opens up a whole can of worms in terms of things that people might do to try to undermine the integrity of the system. And other examples are, the kinds of actual physical attacks on robo-taxis that we've seen in the media. So those are all things that I think we need to think about as we're approaching this problem of design time assurance. So what are some of the things that are out there that we might start looking at in terms of assurance? And I'm just going to give a kind of smorgasbord of answers to that question in terms of things that are out there in the literature. I'd like to refer back to the panel discussion this morning and say that I think that what we ought to count as assurance should be incredibly broad. And there should be a large range of different technologies that we're willing to consider in this context. So not just formal methods, not just traditional safety engineering approaches, but how can we actually bring all of these things together to build safer systems? So just kind of going through the list here. So techniques coming from control theory like Lyapunov and control barrier functions are, I think, a very powerful tool for trying to understand stability properties and invariance properties of the system dynamics. One of the really exciting things there for me is trying to understand how we can take those techniques from the control theoretic setting, which is fairly constrained and well understood, to a system where now we're operating in a much more dynamic environment where maybe there are humans in the environment that are doing unexpected things, or we have stochastic wind models and things like that that make this analytical modeling problem much harder. Statistical analysis is another one, and there I'm counting things like traditional safety engineering approaches definitely need to be a part of the approach, but also more recent things like conformal inference. I think there I would caution that there's some good work there being done, but there's also a lot of stuff that's more along the lines of traditional machine learning. And so actually understanding which pieces of the work on conformal inference can be fed into a more rigorous and holistic safety analysis is a big challenge. Neural network verification has been discussed, and that's obviously an important part. Another one that was mentioned very briefly and that I'd highlight again is the work on assurance cases. So that's coming from NASA, SGT, so people like Ewan Denny and Ganesh Pai. I think that's a very important piece of this, especially in terms of trying to relate the actual requirements, the architecture, and the assurance picture in a rigorous way. Reachability is another one that has a kind of design time aspect where we need to do some modeling and analysis in advance, and we might be able to use to get some kind of design time feedback on the where the system might lack robustness. Simulation-based test and evaluation is a good way to augment actual test and evaluation. And then more traditional model-based verification techniques. So I'll highlight there some of the work from Andre Plotzer's group, and Stefan Mitch's groups. And I think their work on hybrid system modeling and verification and how we can actually try to use that to then in turn relate runtime monitoring to the design time analysis is very important. And that kind of connection between runtime and design time analysis, I think, will become more and more important, especially as we deal with these kinds of systems that are facing, very off-nominal conditions in many cases. So now in my last couple of minutes, I'd like to just tell you a little brief bit about some of the things that we've done at HRL. I'm not going to go into tons of technical detail. I point to a few papers, and I'm happy to, talk to anyone about this stuff in more detail as needed, but, feel free to look at the papers. So we were lucky to be involved in the DARPA Assured Autonomy program, where we worked together with CMU, UIUC, UCSD, as well as U.S. Army GVSC, and we were working with their autonomous ImRazor platform that you can see in the picture there. And that gave us a chance to engage with some of these challenges at a much more holistic whole system level. So some of the things that we did there were related to motion planning, and that's using formal verification to analyze motion planning algorithms for a neural network-based control system, but also things like using neural network verification to analyze the behavior of the point cloud processing perception system. And there I would say that we were fairly lucky because LiDAR and especially the kinds of state estimation that we needed to do on this project was a very well-constrained geometrical problem where we could actually define rigorous specifications. I completely agree with Karina that one of the major problems with applying neural network verification, and actually indeed many of these techniques, is that once you start introducing machine learning components, the likely specifications change that you want to analyze, and they're no longer these nice mathematically well-defined things. We've done some work on that in the camera-based case a few years ago. There, I would say, I think actually the way to go is to better understand the data distributions. And so things like data analysis become much, much, much more relevant once we are working on camera-based perception or more complicated LiDAR-based perception problems. Additionally, I'll just give a plug to the fact that we've done a lot of work on adversarial machine learning over the years. A lot of that was actually focused on adversarial machine learning in a real world context. And one of the things that I would say is a kind of lesson learned from that work is that nearly all of the actual adversarial attacks that someone might want to carry out in the real world are not actually these local robustness issues. They're actually much more hard to specify kinds of robustness issues, and therefore better understanding both the phenomenon of adversarial, the lack of adversarial robustness of machine learning models and how to rectify that, I think will be a very important part of making autonomous systems safer in the future. In terms of next steps, systems engineering, again, I think this is really a systems engineering problem, or it should be. But systems engineering is different in the context of autonomy because we often do have this kind of loop of testing the system and then having to gather data again, which can be very costly if you're actually having to do this on real systems. The role of data, planning for things like those adversarial robustness failures. A possible interesting direction for looking at new research is neurosymbolic. So Dr. Alvaro Velasquez from yesterday was mentioning that, he has this program at DARPA on neurosymbolic, and that's, a possible direction for interesting research in this area. And then finally, multi-agent autonomy. And I'd go back to Professor Cummings' comments this morning about, humans in the loop. It makes the problem totally different. And so involving human factors people and thinking about how humans integrate in these kinds of systems will be incredibly important in the future, in my opinion. And I'll stop there.
Great, thanks. There's a lot that you gave us to think about here. why don't we move on to some of the poll questions, Haley, if you don't mind, and then maybe we can take one or two questions before we move on to Dr. Stanley Bach.
Okay, sounds good. Thanks, Prasad. Okay, next poll question. Instructions are in the chat. Yet again, same code. To what extent do emerging AI technologies pose significant new challenges for AI design assurance that are not yet fully addressed? So I'll set my timer again I'll do 30 seconds, and then I'll keep it open after that. Just want to emphasize your responses are anonymous and very valuable. So hope you take the time. Okay, I'll keep responding on throughout the session. So if you need more time, feel free to respond to the poll for question 15 or 14 for that matter. Okay. We're very skewed towards a large extent. So a large extent do emerging technologies pose significant new challenges, which we've been discussing all day. So not too surprised.
There definitely seems to be a trend on a lot of these the answers to a lot of these questions, but I think that's reinforcing why we're doing this workshop. Well, this is really great. So let's move on to our final speaker, Dr. Stanley Bach. He's currently an associate professor at assistant professor, I'm sorry, at Stony Brook University in New York. But prior to that, he was at the Air Force Research Lab in the verification and validation group, where he won a few awards over there. And so this talk will be around formal verification methods for neural networks. Dr. Bach, can I hand it over to you?
Yes, can you see the slides?
We can.
Okay, perfect. So I'm Stanley Bach. I'm in the computer science department at Stony Brook University. I'm from the formal methods for AI community. So if you were listening to the panel this morning, this means I'm here to oversell what the methods can do to a certain extent. But no, I do hope to provide a little bit of details and specifics on how some of these methods work. And hopefully it's an honest talk about what's currently possible with the state of practice. So it doesn't scale to application yet, but how far can we go?
Hey, Sam. Hi.
Okay, so there's two parts to the talk. I'm going to talk about verification of models first, and then trying to address some of the issues that come up, such as scalability. I'll talk about verification of approximations in the second half. Okay, so let's start with verification of models. So formal verification in general, it tries to prove mathematical properties about different types of systems. So you'll have a model of the system, which tells you how it behaves. You'll have a mathematical expression about what you want the system to do. And then the job of researchers, one class of researchers is to develop verification algorithms. So we're given the model and the property, and then we want some sort of algorithm that tells us either that for all behaviors of the model, it meets the property. So let's say the system is safe according to some definition. And hopefully it provides a proof of that. And otherwise, if it's not safe, it would be great if the algorithm could also provide an example. So show that, here's a behavior of the model where it doesn't meet the property that you want it to meet. So in this context of this group, we're interested in models that contain things like neural networks, as well as things like differential equations, right? So neural networks have been talked about a lot. Differential equations come from the fact that we're dealing with the physical world, right? So the laws of nature are written in differential equations. So a lot of times when you want to make a prediction about what a physical system can do, it's usually given in the form of a model with differential equations. So what type of model are we starting with? So here's an example from, I was at Air Force Research Lab before, so I have a lot of aerospace examples. In this particular case, it's a ground collision avoidance maneuver. And if you wanted to, let's say, even simulate this system, you would have a model that has differential equations in it. And then maybe there's some sort of state machine controller here as it goes through 4 different modes. So in the formal methods community, you would say this is a hybrid system, right? You might have different differential equations, and then there'll be rules on how you transition between these differential equations. So once you have this type of model, what can you do with it? You could certainly simulate the system and see what it's going to do in the future, but a single simulation might not be enough because there's some uncertainty in the system. So you could think of, on the left-hand side here, I think you can probably see my mouse. So there's maybe multiple initial states, or there's different types of uncertainty in the models. For example, the amount of friction that is being used in our simulator. Maybe this is something uncertain. And so we could sample different amounts of friction and run a simulation and see, yeah, they all look pretty good. But even with one dimension of uncertainty, if it's a continuous quantity, you can never exhaustively cover everything, right? And in the real situations, you might want to handle more than one source of uncertainty, right? You might have disturbances or uncertain environments or model errors, things like that. So reachability analysis tries to do this type of set-based simulation, where you start with an entire set of states and then you propagate that set forward in time. And this hopefully gives you stronger guarantees than you would through a simulation-based approach. So visually, it could look something like this. So this is this very simple hybrid system. There's two states, and there's two dimensions of initial uncertainty. So let's say you start in this box. In the left-hand side, you're in this sort of clockwise mode, where the trajectories are rotating clockwise around the origin. And then once you cross x equals 0, you go to this move right mode. And reachability analysis, what it would do, in this case, it's done in discrete time. It would propagate the whole set forward in time. And then once it transitions, it would continue working forward, right? And so the building blocks of reachability analysis are really these set-based operations. So here, all I did was change this threshold, and you can see that the sets become a little bit more complex. There might be a point in time where part of the set crosses to the next mode and part of it doesn't. So then you need to split the set in half. You need to support an intersection operation. If you want to advance the state forward in time, you might need to be able to do a linear transformation if it's a linear set of differential equations, right? You want to check for crosses of boundaries. You need to be able to optimize within these sets, right? And so a lot of the technical work goes into coming up with set representations and ways to support different operations on sets, things like linear transformations, maybe unions or convex hulls or Minkowski sums or subset operations, right? And in particular, we don't just want to do this in 1 and 2 dimensions, right? But we want to do this in high dimensions, because the space of our system, the number of variables we have, it's more than just 2 or 3, right? It's possibly tens or hundreds of dimensions. So you need efficient operations on complex sets, right? That's where some of the research comes in. And so reachability analysis is fine, and that handles these systems of differential equations. Neural network verification can also make use of similar types of set operations, even though it looks like a different domain. And so the most common formulation that it's been talked about a little bit beforehand in the previous talks was this sort of open loop verification, where you have a set of possible inputs and you want to prove properties about the set of possible outputs, right? So for example, let's say all of the inputs to my neural network are between 0 and 1, and I would like to prove that, let's say, output 1 is always the greatest output. So maybe this is like output 1 is some category of classification, and you want to show that the classification doesn't change for every value in this set. So similar to when we were talking about differential equations and running simulations, you could sample from these inputs and run a bunch of tests and see if it meets the output. But with neural network verification, we want stronger guarantees. So we want to do some sort of analysis on sets of states. And so I'll echo what was said in the previous 2 talks, that part of the problem is, how do you actually do this verification? If I give you this, if this is the input, I give you a neural network, an input set, and an output set, how do you actually verify it and make it scale well? But a very important challenge is, even if it scaled to any large network that you wanted, coming up with the spec is also very difficult, right? And so what types of specs have people considered? So one was the ACAS XU system. We saw this 2 talks ago. So this is the neural, it was mentioned in the chat, this is a neural network compression of the ACAS XU system. And so what the system does is it tries to avoid collisions. So the aircraft starts on the bottom here, and there's an intruder coming in. And depending on the initial condition, it might tell the aircraft to turn left or turn right. So it's trying to avoid collisions. The neural network compression, this was proposed in this sort of seminal paper, which I think has like over 2,000 citations now, which is a lot for a formal methods paper. It's maybe not a lot for an AI paper, but for formal methods, there's a lot of interest in this work. And so they proposed this network, and importantly, they provided properties about the system that were feasible, to check using tools. So it's a relatively small network. So to be honest, it's 5 inputs, 5 outputs, 300 neurons and 6 layers. This is not a large perception network. But the nice thing is they had informal properties such as this one where the intruder is directly ahead and moving towards the own ship. So it's a head-on collision. This means that the system should command a turn, right? This is one of the properties. And you can express this mathematically. You can express this in terms of linear constraints. So you can represent it as a set. And then you can consider doing set-based analysis. The other one that's very often used is local robustness, right? So images or classification neural networks are often vulnerable to adversarial examples. So if you take a specific image and you perturb it by random noise times some epsilon where it looks the same, you might get a different classification. You could express this as a set-based property by saying, well, what if this, if I have any specific image, if I take epsilon to be, I don't know, I'm modifying the image each pixel by 1% or 5%. Does the classification change or not? You can express that now as a set, and then you have the input that you would then feed into a neural network verification tool. So how would these methods work technically? So to execute a neural network, if it's the most basic kind of neural network, which is just fully connected layers with activation functions, for execution, you need 2 operations. Affine transformations, which is you have a point, you multiply it by the weights matrix, add a bias vector, that's an affine transformation. And then you have to handle the activation function. So you start with a point and you propagate it sort of layer by layer using these 2 operations. For set-based analysis, if you have a set of inputs, you don't have an input point anymore, you now start with a set. If you can perform these 2 operations on sets, you could then come up with an output set of all the outputs that are possible and then check if it's contained within the sort of desirable set, right? So it's, again, the same fundamental techniques that we had with reachability analysis could be applied in principle to this problem, right? We can do affine transformations, and then to handle activation functions, it depends, if it's a ReLU, for example, maybe you need to split the set in half, right? Or over approximate it somehow. I help organize a neural network verification competition. So given these types of formulations, what the goal of the competition is to hopefully engage industry practitioners and get benchmarks of here's a neural network with an input-output spec, and then engage usually academia and say they have tools, right? And then which tool is the best, right? Because the tricky thing is if you read papers, whatever paper you read, that's the best tool for the job, right? So this is trying to get towards a more fair comparison. You can see we have like over 10 participants. This was, even a couple of years ago, and there's some publications related to this. But if you're even if you're not developing the algorithms, you could still submit your benchmark. And so it's a little bit of work to get it in the correct format, but I think this is incredibly useful from academia to try to get, improve scalability and make sure we're solving practical problems and not just toy problems. So this is all about open loop verification. There's a harder problem, which is closed loop verification, which is if you have not just a neural network, but a neural network interacting with a physical system. How could you prove properties about these types of systems? And so I talked about reachability analysis for physical systems or differential equations, and I talked about open loop neural network verifications, which can take sets from the input of a neural network to the output. In principle, you could think, let's just plug these 2 techniques together. Now we can do closed loop verification. And it sort of works sometimes, right? So in practice, if you have these fully connected neural networks, if they have ReLU activation functions, these are actually piecewise linear functions because you could split along the ReLU regions, and within each region, it acts like a linear function. So the number of splits can be very large depending on the network, but in principle, it's still a piecewise linear function. And then you could take a set, split it into these parts, and propagate each part separately according to the differential equations and sort of repeat. We did this in a work. This is, again, this ACAS XU system. So you have an intruder coming here that's going very fast upward, and the own ship starts here near the origin, but there's some uncertainty in its initial position. And it's also moving upward, but slowly. So the own ship has to sort of get out of the way because this intruder is coming up on it. And if we zoom in on this, what we can see is this is the behavior of the own ship in this scenario, right? So from some initial conditions, it turns right. From some initial conditions, it turns left. And this left-hand side is simulations. And the right-hand side is comparing this reachable set using the set-based analysis. And you can see that there's some correspondence between these 2, which is a good sanity check, I think, always to do. If you zoom in further, though, you start to see some issues, right? Because of all these splits, because these are piecewise linear functions, the sets start to get very complicated. And so they get very small. And you run into real issues in terms of scalability. First of all, it's slow because there's so many pieces. A lot of the polytope analysis tools are built upon linear programming, and efficient linear programming solvers, because you want to run it quickly, they use floating point. And you start to actually run into numerical issues with floating point solvers, which is bad from a formal method standpoint, right? Because you would want a strong guarantee, you don't want a numerical guarantee. So that's a problematic. And third, this is also incomplete, right? This was like one specific scenario. I would want to say that this, neural network compression of ACAS-XU is safe under all scenarios, not just this one, small slice of possible states, right? So it is set-based analysis, but it's unsatisfying, right? Due to really these scalability issues. And so the next part of the talk is trying to address this, and part of this is using approximations, right? So what do I mean by approximation? So if you have a neural network, let's say it's hard to verify because of the scalability issues, can we convert it to some approximation that's easier to verify? And so why would you want to do this? Well, the neural network, it's sort of an approximation anyway. It's learned using data. If you could do something close to the neural network that you could actually prove properties about, you could just deploy this thing on the right-hand side. And then you'd have sort of stronger guarantees, right? So one way we've looked at this is, again, this ACAS-XU system, rather than taking the inputs to the system, things like the velocities and the distances, and directly feeding them into the neural network, we could quantize, or let's say round these inputs first. So if let's say one of the velocities is 715, and it's a long floating point number, let's just round it to the nearest hundreds. So this is going to generally work the same way, right? Because this is an approximation of the real state. Why is this better for verification? It's because it reduces the splitting problem. You no longer have these arbitrarily splits along the ReLU boundaries. Instead, every point that's sort of close to each other will get rounded to the same point, right? You can only split along a quantization grid. And this also means that if you want to verify the system, you no longer need to do set-based analysis. You could actually just execute the network, right? Because everything in this box is going to round to the same point. If you execute the network at this point, you'll know what this whole set does, which means that actually the size of the network and the layer types doesn't matter anymore. This could be a huge network because we can execute huge networks very efficiently. You can use GPUs to do this, very efficiently, depending on the network size. For this small ACAS-XU network, if you just look at the floating point operations, you can execute in batch very quickly because this is what training relies on. It also addresses some of the floating point issues. We're not using linear programming. But the downside is that this will only work when the number of inputs is small to the network, right? Because you end up doing this gridding process, the number of cells is sort of exponential in the number of inputs. So if you have an image-based input with hundreds of thousands of inputs, this approach is not going to work, right? But we also looked at doing this not just in open loop, but you could do it in closed loop. So again, you combine, in step one, you do some reachability analysis, then you quantize, you split, and then you repeat this recursively. And we had some nice results on this. On the closed loop ACAS-XU system, we were able to actually find some faults in the some collision cases in the original system. But I did want to say something about vision systems, so I'll save my last few minutes for that. And so this is an approach that a couple of people have mentioned before as well. So it's really hard to say anything about vision systems, especially in closed loop, because you don't have really a model of the physical world. So in this approach, we would, this line of work, a number of researchers have looked at using generative models instead. So if you have something like an emergency braking system that has an image input, normally a camera would provide this image, and a neural network provides the control. Well, if you train a generative model that can generate images at different distances, let's say, you could apply mathematical techniques to this closed loop system using this generative model plus the image-based controller. How? By sort of concatenating these two together, right? So you would just have this closed loop system going through the generative model and image-based controller, and then you're proving properties about an approximation of the system. How well does this actually scale? I mean, you can do some things, but it's not great. So this is a work from Stanford on the TaxiNet system. So they have a very nice looking image from a simulator, but then when they go to their generative model, they have to downscale and make it grayscale. So this is what the images actually look like. So it's a lot worse, right? It's not quite there yet. And this is because of this, again, the scalability of neural network verification tools. But for these images, you can do analysis, and you could then prove closed loop properties about that. We had some recent work looking at scalability improvements to that method. So this was an image from the Carla simulator for an emergency braking system. And here's what the actual images look like. So again, it's not these nice high resolution images that you would expect, but it's getting better, I would say, to a certain extent. However, again, with these details, there is still a lot of difficulty. It takes a lot of time even for this very downscaled version. So I think this color one is like a transformer-based architecture as well. But you can't prove the full latent space, and there's still, you have to always have an asterisk with any guarantee you have here, because it's only safe with respect to the generative model, right? If in the real world you encounter a situation that the generative model couldn't have generated that image, then of course we wouldn't have detected that using the generative model ahead of time. So there's a lot of improvements you can make to this, even if the methods don't scale in terms of set-based analysis. I think this can be very useful for finding interesting tests. And that's not really fully explored either, but it's a line of work, I think, that's, it does have some value, right? So I don't think we should throw away formal methods quite yet when it comes to neural network verification. So, okay, in summary, we talked about verification of models, specifically differential equation models using reachability analysis and neural network-based models. And then we talked about approximations. So if we round neural network inputs, if it's a small number of inputs, this is a lot easier to verify. And if you want to deal with things like cameras, maybe a generative model is one approach to be able to do something at design time, right? Other than, of course, you have your training data that you can use, but do something beyond that maybe can help you find errors a little bit earlier in the design process before it's out in the field. Okay, thank you.
Wow, thanks so much. This is really really great. We're actually kind of caught up on time now. We don't have any more poll questions until the next session. So why don't we take a break now, let this material sort of digest and percolate in our minds. There are a lot of questions in the chat that we'll maybe try to get to maybe later or offline, but continue to go to break and then come back and maybe can populate the chat with some questions here. All right, thanks everybody. We'll see you in about 10 minutes.
Master, I am time assurance session, and it's my pleasure to be here. I am senior scientist for sensors and perception in the Highly Automated Systems Safety Center of Excellence. You are in for a treat, I think. I will introduce our first speaker. It's J.O. Deschmark, is associate professor in the Department of Computer Science at the University of Southern California and the co-director of the Center for Autonomy and AI. Presentation today is combining neuro, symbolic, and statistical techniques to reason about AI-enabled autonomous systems. And perhaps we have just another second or two. But J.O., when you're ready, the floor is yours.
You are muted.
Yeah, yes, I just realized that. Can you see my slides?
Yes, sir.
Okay, so today what I'm going to talk about is, the title sounds like a mouthful, but combining neurosymbolic and statistical techniques to reason about AI-enabled autonomous systems. And broadly, the reason why we are working on this topic is in the domain of autonomous systems, there's been a paradigm shift in the last few years. Autonomous systems, especially in the aviation sector and even to some extent in the automotive sector, used to be designed using a classical model-based approach where the uncertainty of the environment was relatively well understood and well defined. And you had classical techniques from control theory that were used to address the problem of designing well-engineered autonomous systems. But now, as we move towards the AI-enabled future, we are in this brave new world where we have highly uncertain environments that do not easily lend to modeling. And two buzzwords have become quite common. One is that we are in this paradigm where everything is data-driven, and we are in this other paradigm where we want to increasingly investigate methods that are model-free, which means that we don't want to explicitly build models of these systems, but want to learn them on the fly. So the question that I'm trying to look at in my group and what I want to talk about today is what can we do? What kind of formal analysis can we do? What kind of safety guarantees can we give when all we have is data? So my talk is divided into two rough kind of directions. One, I'm going to talk about adversarial testing, where we are going to talk a little bit about how we can specify kind of these responsibility sensitive safety properties and use AI to actually do some adversarial testing for us. And in the second part of the talk, I'm going to talk more about assurance, where I will talk very briefly about some of the static and dynamic assurance techniques that we have been working with. And then I'll close out with some new work we have on modeling trust in V2V and V2X systems. Okay, so talking about adversarial testing. So here's kind of 10,000-foot view of how scenario-based and specification-driven testing happens for autonomous systems. So you might have a simulation workflow where you specify a specific scenario that you want to test your autonomous system on. Hopefully, you have a high enough fidelity simulator through which you can run your scenario. And you're going to get as an output some system behavior. And usually the system behavior you might inspect either manually or with the help of some scripts to decide if that's the behavior that you want. There have been quite a few efforts at automating these workflows. So for example, I used to work at Toyota for about 5 years, and there we were looking into the problem of requirement falsification, where you have these kind of simulation workflows set up and you want to have ways to express what are some quantitative safety metrics that you want your system to satisfy. And we were working on tools to automatically generate test cases or scenarios that can help you kind of exercise your system and expose some of the worst case behaviors with respect to the safety metrics. So fast forward to autonomous systems. Here, the scenarios that we might want to exercise could be things like there are two cars on a road traveling in parallel lanes on a 3-lane freeway, and there's a third car that's trying to merge in front of one of them while there's an obstacle in one of the lanes, right? So this is an English language description of the scenario. And you might want to see how are the various autonomous kind of capabilities built into these cars react to this particular scenario. So in order to specify what a scenario can or cannot include, I mean, this is probably something that you are more familiar with, is you want to have a nice definition of an operational design domain or an ODD. So you're going to have some rules and constraints that specify the ODD and specify the kinds of scenarios that you can generate that are consistent with your ODD. So just to recap, you have an ODD description, you have a way to generate scenarios, you have a simulation workflow through which you are going to run through these scenarios, and then you need to have some way to check if your overall system behavior satisfies some quantitative safety metric. Now, in this overall workflow, what options, formal methods tools offer is for scenario description, there's work out of UC Santa Cruz and UC Berkeley, where there are tools to programmatically describe scenarios and then hopefully sample scenarios from these programmatic descriptions to run through your simulation workflow. There's some work that my group has been involved in on how can we formalize these quantitative safety metrics using things like temporal logics or state machines for formal specifications to measure the overall system behavior. And there has been plenty of work in the formal methods community, including from my group, on how can we do scenario generation in a more effective way. So traditionally, scenario generation has been either optimization guided, where you use your quantitative safety metric as kind of like a cost function and try to find worst case scenarios that make this cost function have a very high value. or you could turn to techniques from software testing, where you could use things like fuzz testing to generate more interesting scenarios. But what I'm going to specifically talk about in the next few slides is an idea that we have been playing around with on the idea of adversarial generation of scenarios. So here's a specific example where we want to specify the constraints of your ODD and the specifications in a formal logic called signal temporal logic. So in this particular scenario, what's happening is the blue car wants to merge in front of the red car, and the red car, of course, does not want to crash into the blue car. However, as most of us drive cars, we know that if the blue car tries to merge into the red car, basically keeping very little distance in front of the red car when it initiates the merge, or just hitting the red car side on, there's a very little the red car can do to avoid a collision, right? So here, what we want to specify is that the blue car should initiate the merge maneuver to the right lane only when the red car is at least some distance behind the blue car. Otherwise, the blame for the accident should go to the blue car because it initiated an unsafe merge maneuver. So in assuming that the blue car initiates a safe merge maneuver, can we guarantee that the red car always remains some safe distance behind the blue car? So what we are interested in is the system level guarantee, which is as long as the blue car satisfies its constraints, does the red car satisfy its safety requirement of not causing a collision? Okay, so this is kind of the setup. And the idea we have been investigating with my student Shin and colleagues at Toyota Research Institute is given a system under test with some safety metric and an ODD consisting of a number of agents. So here the blue car would be the adversarial agent, the red car would be the system under test. And at each time, we assume that the adversarial agents receive an observation of the car that we want to test, and it's going to take an action in such a way that the adversarial car are going to satisfy its constraints or rules. So they are going to obey the traffic rules, but the action should be taken in such a way that the red car violates its safety constraint. Okay, so here's an example of this multi-agent monitoring. Here's a slightly different scenario. Here, there are two cars that are both trying to get through a traffic light. And just as the blue car enters the traffic intersection or is close to the traffic intersection, the light turns from red to yellow, or rather green to yellow. And when the light is yellow, the blue car is trying to make a decision on whether it should pass through the yellow light or whether it should pause at the traffic light. And the red car behind is trying to make a decision based on what the blue car does. Now, there are a number of different scenarios that can arise. The blue car could decide to go through the traffic light, accelerate, and the red car might decide to follow, which is a straightforward scenario. But a more complicated one is where the blue car decides that it wants to go through the yellow light, but at the very last minute changes its mind, brakes hard to stop before the traffic light, or might change their mind again and decides to go through the traffic light. And in all these very complicated scenarios, if the red car is the one that we are controlling, the question is what kind of control logic should it do? So here again, we might have a number of different agents. So the blue car is an adversarial agent. Another adversarial agent is the traffic light itself. And the ego agent that we are trying to control is the training car. Right, and we have a number of different constraints on the adversary or the environment, and there is a safety metric of don't collide that we want the red car to satisfy. So in such scenarios, we have a method to come up with adversarial policies for generating these kind of corner case scenarios. So here we want to find this policy, which is actions taken by the agents in the environment that respect to the rules of the ODD, but cause the system under test to violate safety metrics. And here we resort to an AI-based techniques. There's a technique called reinforcement learning to solve this particular problem. So for those of you who don't know about reinforcement learning, it's a way in which an autonomous agent interacts with its environment. It takes actions and the environment in return tells it what its next state is, and it gives it a reward. And the objective of the agent is to, of course, maximize its long-term rewards. And here, the way we set up this adversarial agent is by rewarding it whenever it satisfies its own constraints, but also rewarding it when it makes the ego agent fail its constraints. So in some way, we want to look at behaviors in which the environment satisfies all its traffic rules, but the ego car that we are controlling, that one does not, or it has a bug which causes it to collide into possibly some other car. Okay, so here are some examples of this method in action. So to the left, you have this RL-based adversarial agent. In this case, in this particular simulation, you can see that even if the blue car kind of brakes, the red car is able to brake in time. This is just to show you that the adaptive cruise control that is implemented on the red car is not completely stupid and bugged. It does work most of the times. But on the right, we have another example where the blue car brakes and accelerates in a way that makes it not possible for the red car to collide just in time. It's not completely visible from just the videos here, but trust me that the red car on the right video is actually transgressing this D-safe threshold that we have specified as for it to be safe. Also, here's another example. Here, we want to do the lane merging example that I mentioned earlier. So in the first video, the blue car merges into the lane successfully. The red car is able to control its speed and not collide. The orange framed video is where the blue car initiates a merge when it's not at a safe distance. So here, though the red car crosses the D-safe threshold, we are not interested in this scenario because it was the blue car's responsibility in this case of, it evaded its responsibility of being safe. The blame was on the blue car. But on the frame to the right, which is in the green square, you can see that the blue car initiates the merge maneuver when it is still some distance away from the red car. Longitudinally away from the red car, but the red car cannot stop in time, and it actually does crash into the blue car. A similar example for the yellow light here, we can successfully demonstrate that the blue car passes through the traffic light, but the red car gets kind of stuck in the intersection because its control logic is not designed well, and it gets confused by the actions of the blue car and gets stuck in the traffic intersection. Okay, so hopefully this kind of gives you a flavor of the kind of adversarial testing approaches that we have been trying. We have been trying to work with real planners, but of course, one of the big challenges that the earlier panel also alluded to is academic researchers are often hampered by the lack of access to real world planners. So I would be very interested in collaborating with people who have access to these kind of panels to try out our methods on real systems. So far, we have been playing with planners that were made available to us through our industrial collaborators or some open source ones. All right, so switching gears a little bit, I want to talk about neurosymbolic assurance. And I think one of the earlier panels raised a very interesting point that formal methods can sometimes be viewed as overselling. But I want to argue a little bit more that assurance is not just about formal methods. In fact, I would argue that assurance is a group effort. It's a collection of techniques from things like theorem proving, which helps organize the assurance case, formal methods, which focus on logical specifications, and specific methods like the reachability analysis that Stan was talking about, or some of the methods that Michael referred to. Some of these methods can be used to automate the proofs of correctness of smaller components, smaller modules within the system. But also there is a lot of value in looking at techniques like failure modes and effects analysis, fault trees, systems theoretic process analysis to kind of reason more holistically about failures of the entire system. Whenever you have a human in the loop with an autonomous system, you absolutely have to think about human factors. And what I want to also kind of shine the light on is while AI ML techniques have focused on kind of bringing out the next new shiny object, as Missy called it earlier, I think you can also use AI/ML techniques to help generalize and scale reasoning. And this is the class of neurosymbolic techniques that I want to talk about a little bit in the rest of the time. So again, going back to the assurance flow for autonomous systems, there are several different ways you can reason about assurance. So here's again the scenario-based simulation workflow that I showed earlier. And here you might be interested in some kind of a static assurance of the kind that what's the probability that for a randomly generated scenario, my system is going to satisfy its safety metric with some robustness value delta with a probability of greater than 1 minus epsilon. Okay, so one interesting question here is to reach this level of assurance that you want. If your epsilon is 0.0000001, 10 to the minus 8, for example, how much data do I need to kind of show that this probability guarantee is met? Okay, so I'm going to talk about a specific technique that we have been working on in collaboration with some folks. So with my students, and also Chuchu was a collaborator on this work. So here we have a technique that uses conformal prediction, which basically gives us a way to sorry, my presentation seemed to be stuck, but it's okay now. It allows us a way to kind of quantify how much data do you need for the level of assurance that you want. So for example, if you have 10 to the minus 8 as a level of assurance, you would probably require something that is in the order of 10 to the 8 trajectories of your system to give that level of assurance. And using this technique, we have also been able to kind of characterize what are the safe and unsafe regions in the design parameter space of your system, using, again, this idea of conformal prediction and its variants. I'm skipping over the technical details of how this works, but I would invite you to read some of the papers or have some offline discussions if you would like to learn more about this.
And Joe, we're at about the 2-minute mark, if that's okay.
Yeah, I think I'm going to go over this faster now. Okay. The other thing that we have been working on is dynamic assurance, where essentially we want to not only reason about the systems offline while we are developing it, but also at runtime. So can the safety metric or design assumptions continue to be satisfied in the future at a desired level of assurance? And we can again utilize these statistical tools and combine it with runtime monitoring to give you guarantees of how likely is it that something will fail in the future. And we have tried this again using the Scala simulation to show that for safety metrics like cross-track error, responsiveness of the controller to cross-track error, using some off-the-shelf trajectory prediction techniques, we can reason about this. One thing I wanted to highlight here is very often in many of the formal methods work that we do, we prove things about models, but that's kind of a gap, right? We want to prove things about the real system, not just about models. And one benefit of using techniques like conformal prediction is that there are robust versions of these that can help address the sim to real gap. So for example, if there's a distribution shift between the model on which you're trying to get results and the real world system, then you can also inflate your guarantees in the right way to handle this kind of shift in the distribution. One final note that I want to talk about is models of trust. How do we trust AI that we are using? And for example, in a V2V, V2X based system, you could have agents such as cars or roadside units that report the state to some kind of a coordinator, or they might report the state of other agents in the system. And the coordinator is going to receive observations from agents. It's going to give a sequence of commands or suggestions to agents and can observe some agent actions. But everything that's in the red on this slide could be fake, or it could be, and here by fake, I don't mean malicious necessarily, though that's certainly a possibility, but it could just be because of a faulty sensor or because of a perception error. And the question is, when these things are fake, how can we be sure that the system is going to be safe? A big assumption here is that if everything is trustworthy, if everything is as it should be, the agents will safely achieve this objective. So I'm assuming here that there is some proof of this kind, but the question is, what if the systems that are communicating with each other themselves are not to be trusted. And one of the things we have been looking into is using this kind of a epistemic logic, a logic of knowledge called subjective logic, to update our trust in agents. And the main idea is to come up with this notion of a trust score, which is much like your credit score. And if your agent is low in trust, for whatever reason you don't trust them, you want to take actions that are more conservative around them. Whereas if you highly trust an agent, you can prioritize actions that are more performant. And using this idea, we have been looking into these trust-guided control applications, like extending the autonomous intersection management idea to cases where you could have a mixture of these trusted models. So again, as the figure shows, the untrustworthy car has a bigger buffer around it. So you would want to make it go through an intersection with more space around, whereas a trustworthy car is going to go through the intersection with a smaller buffer. We've also applied this to neural network-based perception, where we have been working with Georgios Fenekos from Toyota on coming up with these new quality temporal logics to reason about perception and combine it with physics-based reasoning in this quality temporal logics. So for example, here, if you use a quality temporal logic-based proxy monitor, we can avoid an accident even when the neural network fail to recognize a pedestrian in time, by basically recognizing that in some cases the neural network is less trustworthy than others, and where it's less trustworthy, the car should take more conservative actions. Again, I would be happy to chat about this offline. Just to conclude, I talked about neurosymbolic scenario generation and testing and neurosymbolic assurance. And there are quite a few valuable formal methods tools that you can use to solve smaller problems to build kind of a bigger assurance tapestry. And I want to leave.
Thank you, Professor. If it would be okay, we'll leave the slide up for a sec, let everybody take a look, and perhaps switch over to Ian for the Menti poll, just so we can stay on time. I know it's getting late in the day. It's a tremendous presentation. Thank you so much.
Thank you.
Okay, Ian, over to you.
Sounds good. Thank you. So real quick, I'm showing the Menti instructions again, just in case anyone hasn't joined. So it's menti.com. And then the code is 81205112, or the QR code. They're both available on this slide. So for question 16, we have another statement, which is continuous performance monitoring and maintenance are integral to AI operation time assurance practices. So I'm going to go ahead and turn on responses and put a 30-second timer on here. And so we have our options again are strongly agree, somewhat agree, neither agree nor disagree, somewhat disagree, strongly disagree, or don't know. And again, you're encouraged to participate. Your answers are anonymous. And even if you don't know, that's definitely good information to know.
Okay, thank you, Ian. And if you could, if I could have the next slides teed up, please.
And real quick before I turn it back, so we have a lot in the strongly agree and somewhat agree categories. So with that, I'll send it back.
Okay, our next speaker, it is my pleasure to introduce Johan Schumann. He is Senior Tech Fellow at KBR Wiley and working with the Robust Software Engineering Group at the NASA Ames Research Center. His presentation will be runtime monitoring and assurance for AI/ML-based systems. Johan, over to you.
Okay, so thank you very much. So I'm talking about runtime monitoring. We'll introduce the topic and pretty much give a short executive summary here. It's the runtime monitor is pretty much a system sitting next to me and watching my presentation and saying, okay, once you started the presentation, you have exactly between 12 and 15 minutes to come to the end. So pretty much, I'm not talking about intelligence of myself, but this is a runtime thing which monitors important properties about safety, about performance, about security, while the system is running after deployment. So to motivate a little bit more, a couple of years ago, I was on a flight from Boston to San Francisco, and a couple of hours in the flight, I woke up and saw this map display in the seat in front of me. So I kind of was disturbed. The stewardess asked the pilot. The pilot looked out of the window, said, "The sun is on the left-hand side, so we are okay." So what is the takeaway thing from this example is a design time verification obviously cannot read out all possible errors and failures. This might be a software problem, this might be an operational problem. And second, it's for runtime monitoring, for runtime assurance, it's important to be able to take in information from different systems here, like the pilot looking at the sun, so pretty much not relying on GPS or the flight plan. He really kind of went back to the basic principles to come up with a important confidence measure on the decision. So I'm talking here specifically about a tool called RTU2, which stands for Responsive, a reliable, unobtrusive unit. Runtime monitoring, it's important. It must respond in real time. So it's while the car is driving, while the aircraft is flying, it needs to respond immediately. It should be realizable and unobtrusive, because you don't want to, let's say, annotate your software, annotate your neural network, or otherwise mess up with the vehicle control software, because this is a safety critical issue. Our system, which is available as software and FPGA configuration, as well as for coprocessors, combines metric temporal logic observers, Bayesian network reasoners, and model-based prognostics. So let's have a quick look at these various ingredients, and then we look why this is important to have all these monitoring ingredients to deal with AI/ML applications and components. So runtime monitoring system in a nutshell is looking like this one. The system on the right-hand side, the monitoring side, receives signals from the system here. Because I'm working at NASA, it's obviously an aircraft or a spacecraft, only receiving signals and then doing signal processing, and then it has 3 different engines for temporal logic, Bayes reasoning, and prognostics prediction. So let's look at the various ingredients. Temporal logic is pretty much, in our sense, a logic which can deal with Boolean formulas like and or not, and additionally has temporal operators. So we can say, for example, on the left-hand side, always within the next 4 seconds, P must hold. So if, let's see, on the right-hand side, there's a drop out of the signal within 4 seconds, then this formula is not valid. Another important operator is eventually, sometime, this needs to hold. So the system, the machine here, can deal with past time, so we talk about what has happened, but also with future time logic, and has, this is just a technical thing, asynchronous and synchronous observers. That's because we don't have a crystal ball. So let me just show one example here, which needs for monitoring. If the battery current is high for the last 10 seconds, we expect that during that time we have a consecutive climb for at least 3 seconds. This is just for, let's say, a fixed wing aircraft. And so we write this down in this kind of logic. And RTU2 would receive battery current as signals and battery voltage, and then could at each point in time say, okay, this formula is true or this formula is false. So this is very helpful for monitoring traditional software, for monitoring traditional systems. Now we can say, okay, we need to fly over a mountain. takes 10 minutes to fly over the mountain, and obviously I want to have my battery be strong enough to fly me over the mountain. So we could write this in temporal logic like this one. However, that's not good because we don't have a crystal ball. We only can, after the 10 minutes, say if this formula is valid or not. With a three-value
Johan, I apologize. Are you on slide 5 in your talk? We may be having a problem with the slide advancement here.
Oh yeah, I see here. I'm already at slide 8.
Perhaps.
Yeah, but stop the sharing and share again.
Yes, thank you.
Let's see if that. Okay, so this is runtime monitoring in practice. Some monitor that's Daniel, that's you telling me, okay, something is wrong. You need to react immediately. Okay, so we were talking about when flying over the mountain, which takes, let's say, 10 minutes. We could write this very well in temporal logic, but it doesn't help us because we don't have some way to look into the future. However, and the previous speaker already mentioned this, using model-based prediction, model-based prognostics, which can provide important information about important properties like this state of the battery. Looks like those slides are not shared.
Yeah, Johan, I am sorry. We appear to be having technical difficulties. If you could try to share and reshare one more
I'll just do again.
The runtime assurance, AI assurance workshop has been too successful for DOT teams. We can't handle all this enthusiasm.
I'm sharing, but I don't know if this by this.
Mrs. Taylor, I'll go ahead and share your slides, and then we can just say next.
Okay,
so I have your slides right here.
Yeah, so I would say.
Oops.
You just go to slide 8.
There we go.
Okay, perfect. Thank you. So this is pretty much the reason. One ingredient of the RTU2 runtime system is that we have a model-based prediction prognostics capability, so we can look forward and find out probabilities on what things will happen in the future. And if you go to the next slide, something which also is very much important for dealing with AI systems is be able to reason with probabilities. And for that, we integrate Bayes reasoning with temporal properties and provide an efficient constant footprint implementation, because everything is running on board. We can't have a huge costly reasoning engine. Therefore, we have a very efficient implementation of Bayes reasoning, which we can use to combine information from several subsystems and provide some principled probabilistic output on the state of the system or the state of the components. So let's go to the next slide, please. So this RTU2 system has been used for a bunch of mainly drones here for safety monitoring, performance monitoring, security monitoring, failure diagnosis, prognostics, and autonomous decision making. So this is pretty much a system existing and being used for traditional systems. And now let's look on the next slide. What is needed to to monitor during deployment time a neural network or an AI system. Number of speakers before me did a very good job on explaining and talking about the TaxiNet or autonomous centerline tracking system, so I don't need to talk anything about more that. Just in a nutshell is, why is this important? AI/ML can produce noisy or arbitrary results, can produce wrong results. It's inherently probabilistic. However, AI/ML is usually not non-deterministic. This is with respect to the computer science view, which they think non-deterministic has always random number generators in there. We found out that the controls engineers speak about non-deterministic as being non-Markovian. So one thing which we found out is notions of special properties need to be really carefully defined. And of course, everyone knows this. These components lack explainability and interpretability. So as a last line of defense, we really think that runtime monitoring, both on the component side, so very much directly monitoring the neural network or the AI component itself, as well as on the system level. And the previous speaker also mentioned the VNV on the neural network itself and VNV on the entire system. So this nicely fits in here. So on the next slide, please. I just list kind of categories of properties which we are monitoring with our RTU2 system and which are specifically suited for monitoring of a neural network-based system. So you see here, if we start with system safety, for example, saying, again, looking at this TaxiNet centerline tracking system, when the aircraft is, let's say, near the right border on the runway, the aircraft shall not move further to the right for an extended time. So what we see here is we have a temporal formula underneath this requirement. And we also can have probabilistic things that the further you are out, most likely the more stringent you have to combine. Then we talk about component safety. For example, the DNN output values shall be reasonably limited. We can talk about system performance, that the aircraft is actually performing the task within a reasonable time. Again, here, temporal logic. Or component performance, like the DNN outputs between consecutive images should not jump around, which still might be safe, but it would lead the aircraft to more or less zigzag around on the runway. Then, and this is again taking in external information, like environmental operational conditions, saying, okay, this only should operate between 9 a.m. and 2 p.m. local time. We also combine this with diagnostic failure detection, failure modes. So we have might have system failure modes and might have AI/ML component specific failure modes. So system failure mode might be the camera might have some problem, or the braking system or the steering system might have some problem, and the AI/ML failure mode analysis might directly talk about the neural network is not, for some reason, not performing as expected. And so now we have a bunch of properties which we can efficiently monitor. And now one would ask, hey, what I do? Is there just a usually one would say, oh yeah, let's light up a red light in the cockpit, but in most cases there is no cockpit. So what to do with that information? On the next slide, please. This is very much a runtime assurance architecture where R2U2, our runtime monitor, is a central component. So this architecture, which is based on upcoming standard of the ASTM F3269 subgroup, looks like so. On the going from left to right, the AI component is getting input signals and producing some output. The monitor also looks at these input signals and decides if the output of the AI component is safe or not. If it decides it's not safe, then the monitor is able to switch using this RTA switch and activate what's called assured fallback position. So this is the original architecture, mainly, I think, still focusing a lot on fairly traditional systems like software-based systems, not necessarily really the Android AI components. So on the next slide, we extended the architecture, very much allow the monitor to look into the neural network, where it's or into the AI component. For example, get out some confidence values, things like that, in order to actually get some more information to make a decision. And also there might be different AI components either working in parallel to produce some kind of redundancy. This is also an approach which can be used for increasing certification for DAL levels in, let's say, in the DO178C world, or it can switch over to other AI components if they perform better. So it's a mixture between the runtime monitor to deal with safety aspects, and a runtime optimizer which can switch between components. So if you go to the next slide. So I was talking about this R2U2, which is responsible, realizable, unobtrusive unit, both for system and AI ML component runtime monitoring. And the ingredients, which we think is all necessary for doing monitoring of AI components, is metric temporal logic, Bayesian reasoners, and model-based prognostics. And I showed the kind of a certifiable runtime assurance architecture, which kind of can incorporate this R2U2 component to pretty much keep the AI component in check. So that's, please, on the next slide is just some publications and the final slide. So thank you.
Okay, Johan, thank you. That was an excellent presentation, and we are right on time, perhaps even a moment for a question, and I do see some in the chat. One question from Jason Rupert. What was the safety assessment or level of rigor or development assurance level for the R2U2?
That's a very good question. Originally, the R2U2 was developed as a research prototype, so we didn't follow any high assurance process, but recent developments and future developments actually will produce certifiable, so following some traditional DO178C complying processes to come up with certifiable component.
Okay, thank you, Johan. And there are also perhaps another question or two in the chat if you would like to take a look and answer there. I will now hand it over to Ian for our Menti poll.
Thank you. All right, so we have question 17, which is how effective are existing practices for predicting and managing the operational lifespan of AI systems? Let me go ahead and open up the response, and I'll set another 30-second timer. So I'm going to go ahead and show the results and turn the responses back on. And just a reminder, all the responses will be on for these questions until the end of the session. So for this question, we have a pretty obvious winner at not too effective. Few 3 on the left, few on the right was somewhat effective, and not at all effective, and then 6 with don't know. So.
All right, thank you, Ian.
Thank you.
And if I could have the next set of slides teed up, please. Or I'll go ahead and introduce our next speaker. It is Dio Diniz, a principal researcher and the technical director of the Assuring Cyber Physical Systems Directorate at the Software Engineering Institute at Carnegie Mellon University. His presentation is Resilient Mixed Trust Assurance for Autonomy.
Perfect, thank you. Can you see my slides?
Yes.
Perfect. Okay, so today we're going to talk about this mixed trust assurance. Hold on. Give me one sec. Okay. So basically, let me start by kind of stating the obvious is the challenges of assurances in autonomy, right? One of the key problems here that we have is this new model of computation that is not a traditional model that we are used to verify. And we have seen over these presentations different ways to adapt to this new model of computation. But in addition to that, we also have an uncertain environment. And this uncertainty creates new challenges that we need to really go after and try to take into account. And beyond this, we also are required to preserve safety through failures in sensors, failures in components, hardware components, software components, and the like. And not only these failures per se, because it's always easy to have a perfectly safe car when it's parked in the garage, but we also need to preserve performance through failures, right? So all of these are the challenges to which we have been trying to provide an answer. Our approach is based on what we call the mixed trust assurance. And the idea here is that we recognize that the systems are composed of components that we can verify and we can trust, but there will be other components that we cannot trust. And therefore, one of the approaches to use, the one we use, is actually to create an enforcement framework around that. Right? In this case, this enforcement-based verification, what we will do is identify these safety properties, and by design, by strategy, we leave as much as possible code unverified, right? And this is actually key to enable scalability, because we want to provide an aspect that is scalable. And what we do is we add these enforcers that we have been presented before, and those are the ones that we formally verify. But this verification for us, because we are talking about cyber-physical systems, need to have multiple aspects. For instance, logic to produce the proper value, the correct value, but also in time to produce it at the right time, and the physics effects of this value, as Stanley Back was presenting in the past. I mean, how do we do when we need to verify not only the output produced, but also the effect in the physical environment, right? So all of that is part of the challenges and the target of our research, if you will. And finally, because we want to make this very genetic, the failure of the entrusted component may not be only because we are implementing this in a component that is machine learning, but also can be because either can be even a malicious element, a virus, or a failure in the implementation that can actually kind of interfere with the trusted components. So protection is important for us as well. So to start with, when we talk about values, our model has been creating this safe space where we actually have a safe space that actually we recognize these different states and transitions across them. And we actually, within this safe space, we also recognize what we call the enforceable states. So these are the states over which we can recover, we can kind of create a transition that will bring us back to this safe state, and that we can actually prevent getting out of this unsafe state into the unsafe region, if you will, right? So for that, what we do is, as is any of these frameworks of enforcement, right? We recognize these unsafe states, but enforceable, and the enforcer will watch for the output to see whether an unsafe transition may occur, and it will undo that and return it to the safe state, right? So obviously, what we do with this is kind of develop this model in the, I would say, value environment, if you will, and we actually are able to implement some model that we can verify based on our particular implementation, in this case in SMT. That is one of the many tools that we have used. But going beyond this, of course, because it's a theoretical system, then one of the elements that we have used, or technique that we have used to develop these enforcers, is the use of Lyapunov functions that basically will do very similar kind of reasoning here, where we have a safe state and the recoverable state. But in this case, we use the Lyapunov functions to really create this cone, where we will be able to say, as soon as we are in this region, any misbehavior can be recovered and kind of go back to the traditional set point that we can recover. So once we have this kind of frame of reasoning, what we can do then is create trajectories of the mission, if you will. So these trajectories will create these balls in the multiple dimensions that we have, and that we can kind of trace the trajectory and discover that if we have a failure, we can actually identify the failure and recover from it, taking it to the next set point in the trajectory to be able to kind of continue our mission, right? So this kind of framework allows us to implement this in this example. For instance, in a drone that is following the trajectory that you just saw, and allows us to kind of continue doing this reinforcement. And we have applied this enforcement not only for components implemented with machine learning, but can be also applied for components that can be attacked, in this case for cyber security reasons, if you will. So going forward, then the next step is to say, well, we know that our system has this sensing and actuation transformation, if you will, right? And what we are trying to look is what are the actions that we are that we need to verify. And of course, what we said in the past is that if we have some bug or attack in this untrusted component, then actually we cannot trust the output, right? Then therefore we have this monitor, if you will, this enforcer. But the enforcer itself, the question is, can we really trust it? And this is where I would say the protection aspect of things come into play. Because, for instance, we can, if this is an attack, basically, even if we have a verified component, if this verified component is corrupted because of a bug that kind of infiltrated the memory or an explicit malicious attack, then this will be this will actually make this component untrustable. So of course you can say, well, we can create with the protection memory mechanism that we have, we can add such a protection and make sure that it's not attacked. But interestingly enough, that is not enough. And part of the reason why this is the case is because typically in a real-time system, in a statistical system, in a control system, we need to have this periodic execution that is always sensing and correcting kind of the position and trajectory of the system with multiple actuations. In such a case, it's possible that one attack to one of these components, right, that is not protected because the untrusted component can delay the execution of our output. And actually, even if we evaluate that the output is correct, it may be too late already because of the delay caused by the untrusted component. So what we have is a problem that the system or the timing of the system cannot be trusted now. So what can we do in this case? So what we did is we added the traditional watchdogs, if you will, that is basically a timer that is continuously verifying whether an output was produced or not. And if it's not produced on time, then it will produce an automatic default step action. So you can think of this, for instance, for the case of the drone, for instance, a hover action while we decide what to do within this situation. So this combination of the protection and the double execution, if you will, both the regular task and the watchdog task that we call the hyper task was implemented in what we call mixed trust task, right? Where one piece will run, or the piece that is untrusted will run in the untrusted virtual machine, and the other one will be running in a trusted hypervisor, right? So we combine then these two particular, I would say, schedulers. We coordinate the schedulers. We prove the coordination happens properly, and we run this hypervisor, if you will, and we verify the hypervisor fully starting from the instruction set of the computer, if you will. But of course, as I mentioned before, one of the challenges in autonomous systems is that failures are part of the equation. And we need to make sure that we really kind of take into account these failures, right? So for instance, one of the problems is, and this is common and well known in autonomy, that is, for instance, a publication from Daimler that is called Safety First for Autonomous Driving, and talks about this traditional nominal operation, minimal risk maneuvers and minimal risk conditions, that we need to do something about the graded operations whenever we have a failure. Right? So, of course, part of the challenge here is that once we have, for instance, a good case and a verified behavior, if you will, when we are using a particular sensor, but then we have the possibility, or I would say the backup, if you will, that using a different sensor for instance, in this case, of obstacle avoidance or obstacle automatic braking, right? The conditions for this guarantee will be different. So we need to have some way to do the proper transition from one, I would say, in this case, sensor to the other, based on the failure conditions that we have, right? In this case, it's a very simple example in order to make this transition simple. And the transition will be as soon as we discover that we are out of the light, that the brake is failing, then we'll start braking until we reach the conditions that we have, right? The conditions of the maximum speed that we can tolerate with the sonar, right? But during this transition, it means that we need a special enforcement for the transition, right? And this means that now we have a state machine where the state machine has these different modes. And while we have an enforcement scheme for one mode and another mode, we need to have a special enforcement transition, if you will, right? So we developed the model to do the timing verification of this new transition and kind of created the new schemes to do the transition in this case, right? Now, one of the things that I want to highlight here is that because now we are talking about certain physical systems, we need to do analysis from different aspects for which the different, I would say, scientific communities have created multiple analyses. So one of the things we discovered and we have worked on and keep working on is that the integration of the results of multiple analysis of a system need to kind of look at the assumptions, cross assumptions between these analyses, and make sure that those assumptions are not broken or do not contradict with each other. We have organized this in kind of, I would say, an assurance argumentation, very similar to an assurance case. But in this case, we are kind of using a deductive logic to be able to kind of follow assurance claims, for instance, close to certification claims, that we can actually discharge as we use different analyses, right? And the assumptions of the analysis can be discharged by further analysis or even by the complementary analysis of those, right? We have actually been working on in a particular work group called the ASER-W. It's assurance evidence for continually evolving real-time systems, where we kind of, as an experiment, we develop a model to verify an instance, a flight instance in the Taiwan incident in 2020. So you're welcome to look at that and give us some feedback, right? To conclude, basically, autonomy is difficult to verify, of course. We know that, and that's what we are doing here. There are multiple elements that we need to take into account. In one of the potential ways to go forward, as one of the elements, not the only one, is talking about this mixed trust. Things that we cannot trust, we need to enforce them. Things that we can verify, we should trust and protect. And we need to integrate the multiple levels of analysis that CPS needs to be able to prove properties of, right? And of course, we need to deal with failures. Failures are part of the equation, and this is something that cannot be ignored. Thank you.
Okay, thank you, Dio. We are right on time. In fact, we perhaps even gained a couple of minutes. So time for questions. There is a comment in the chat that I think perhaps we could ask, that we could turn into a question. I am curious to learn more about how the Bayes reasoning is then validated. So can you draw out that idea perhaps for us?
Yeah, I'm not using Bayes reasoning here, so I'm a little bit confused.
Oh, I'm sorry.
I think it's for Johan.
I'm sorry. Yeah. Okay. I apologize. That might have been a question. It came up during our time, but perhaps was referring to the previous speaker. I apologize.
That's okay. Yes.
Okay. So please don't be shy. We have a moment. If anybody has a question in the group. Well, okay, Dio, thank you again. If we were in person, I would ask for a round of applause. So everybody may go ahead and clap in their own office, but don't take your self off mute. We have a few minutes now. At 45 minutes past the hour, you can all come back for reflection and wrap up. I also want to let the group know that slides will be provided to all registered attendees. That there will be a link at the end of the session today for a website where materials will be posted. And of course, for our speakers, that is only if you have given your consent to have your slides shared. And let's see with that. There is no Menti. If you were excited about a final Menti, I am sorry to disappoint you. So let me thank again Jo, Johan, and Dio for a tremendous session. And I will hand it over to the break.
All right, welcome back. This is the reflections and wrap-up portion of our workshop. During the first part of this session, we'll share key takeaways and reflections from each of the panels and technical sessions from the last 2 days. So whether you've been with us from the beginning or recently joined the workshop, we're going to briefly cover all of the topics discussed by our speakers. From there, we will transition to a discussion with speakers from FAA, FHWA, and FRA. I will introduce them after we run through all of the session highlights and key takeaways. Please note that the highlights and reflections I'm about to share reflect topics discussed and raised by our academic speakers and do not reflect priority, future actions, or an official USDOT position. We tried to keep the overview brief for this session. A longer summary will be sent following the workshop. You'll be receiving communications about that. So the first panel that we had yesterday, we heard from USDOT, Federal Aviation Administration, DoD, and NASA and their perspectives on AI for safety. So what we learned is that each organization has stood up AI safety programs that work with industry and the academic community. We heard that the development of standards, and this is going to be a running theme, the development of standards is critical, but it's challenging due to the exponential nature of new technologies. So the rapid evolution really requires continuous update of standards. Also critical is the work with industry. So in order to help drive this research forward in the use of AI for safety, we really need to focus on collaboration between public and private communities in transportation, as well as raising awareness and educating the public on the capabilities of AI systems. This will help dispel any miscommunications or misconceptions or fears that may exist or prevent them from occurring in the future. Digging a little bit deeper, there are a few additional questions and areas for further investigation that were generated from this session. So the first was workforce development related. Talent retention and workforce development is particularly crucial for government agencies. This includes bringing in AI experts and determining approaches to keep brain power. Further, in the US, continuous engagement in international standards in the development of AIA will be imperative. And we've heard this next one throughout the workshop. Again, collaboration is key between the entire academic, government, and industry communities in transportation. This can help reduce the barrier, the large resource barrier, to help push forward more research in AI for safety. Finally, the last reflection here, it's really important to continue investing in AI assurance to help drive safe AI forward. So that's the first wrap up for the first panel. I'm going to move pretty quickly here because we have a lot to get through. So the first technical session that we heard yesterday focused on AI risk assessment and mitigation. Highlights from the session include the following. Fear of AI deployment doesn't necessarily reflect risk accurately. So we heard the example of fear in aviation to deploy ML-based perception, adaptive control, and pilot override systems. A powerful use case is found in enabling persistent ML utilization in real time and offline. This allows adaptation, especially if there's no human backup, and AI can be that safety backup. Safety is more than just net average safety across the entire population. The increasing use of AI brings risks across system layers that need to be considered. And to help with the uncertainty of AI systems, we can look to VitaX to help share data. Due to the voluntary nature today, industry standards are underdeveloped and underutilized. So moving towards the reflection section, so investigation is necessary to determine the full scope of risks for AI. We also heard that we need to better define the meaning of safe when it comes to AI. So this includes defining it at the disaggregate level. VitaX can be leveraged to improve situational awareness and reduce uncertainties. There's an opportunity in the future, we heard, to exploit the V2V link between cars and expand to aviation, as well as to allow better coordination and better situational awareness. Proactive mitigation of risk may be accomplished through standards development, lifecycle management, formal analysis and verification, as well as safety-driven learning. Support and engagement in safety standards development may help to build a safety case for non-deterministic AI systems that are difficult to verify with traditional methods. So for our technical session on AI data assurance, we first heard training data must be representative of the driving scenario space and must include critical edge cases, not just the common situations. Data bias in transportation can arise due to unbalanced sensor deployment, overlooking unique transportation scenarios by typical sensing technologies, and natural long-tail distributions. We really need to capitalize on predictive strengths of AI and causality interpretation strengths of statistical modeling for safety research. For instance, using statistical modeling to quantify uncertainty and evaluate prediction outcomes and gain insights. We also want to use insights gained from statistical modeling to inform training and recurrent enhancement of AI predictions. So digging a little deeper into this session, a couple of questions and areas for further investigation include, periodically bringing diverse groups together to reach consensus on what constitutes bias. So what constitutes a bias varies by stakeholder group. It might evolve over time. So we need to really bring in diverse groups and perspectives to reach consensus and monitor bias continuously. Second bullet here, collect or create data for edge case scenarios for safety research. So as resources are constrained, we need to maybe consider pooling resources to collect edge case data or create realistic synthetic edge case data. We also want to maybe consider bringing in experts from various groups, from federal, public sector, academic research communities, and industry to identify edge case scenarios, which may differ by the problem at hand. Right. Our second panel this morning was on AI research needs and priorities. So we heard a lot of great insights and perspectives from our panelists and our moderator. The first being that federal funded opportunities are really crucial for the academic community when it comes to AI assurance and safety research. And AI assurance is not just the technology aspect of safety, it also must factor in the social, psychological, and human factors components. Researchers want to solve the real-world AI problems. However, funding, access to funding, data, and direct knowledge could serve as a barrier. And then building general AI literacy is absolutely critical when it comes to workforce development and ensuring equity. So in terms of reflections, we identified through the discussion that new verification methods are needed. So existing formal verification methods fall short of AI safety assurance for today's massive AI models. We also heard that establishing an AI community of interest could be beneficial in helping create more opportunities for direct engagement between the public and private communities in transportation when it comes to AI assurance research. We can also help from the government standpoint by collecting useful data and information and sharing it publicly. And then also subsequent workshops, which we will talk about towards the end of the day today here, could potentially explore, what falls under the umbrella of assurance and really diving into that topic in future sessions. Our first technical session this morning was focused on AI design time assurance. We really dove into different techniques that are in use for deep neural network verification. However, each one has its own set of challenges, is what we heard. Generalizability is critical, especially when it comes to autonomous systems. And when it comes to design time assurance, we really need to carefully examine requirements, understand the role and impact of training data, verify and test the models, plan for contingencies, and build robust models. And when it comes to building robustness, we need to build for adversarial robustness to make autonomous systems safer. And then the final highlight here, so verification of neural networks, it really does require verification of models as well as verification of approximations. Reflecting on this session, so a couple of questions and insights that emerged is exploring the right use case for design assurance technologies in safety argument and the full safety processes will be something that we could potentially consider. Also, enhancing adversarial robustness of AI models. This could potentially benefit the development of specialized tools and methods in AI design time assurance. It was also brought up that there could be a benefit to building a community of practice or multiple community of practices focusing on defining robustness, as well as other properties for verifying neural networks. And then finally, design autonomous systems using neural networks that are safe, robust, and interpretable will be crucial. Right, and then the operation time assurance technical session that we just heard earlier today. So one of the topics that was brought up is the recent paradigm shift from classical model-based approach. In this case, there's uncertainty was relatively well understood to the now model-free and data-driven approach in uncertain environments. Scenario-based testing workflow could be useful to find corner cases. So combining methods for verification and testing, such as neurosymbolic, formal methods, statistics, and AI, may help with operation time assurance for autonomous systems because it would allow for the inclusion of rules and constraints, allow for stochasticity, and focus on failure cases. And then finally, for the highlights portion, runtime monitoring and assurance of AI systems should respond and must respond in real time, be realizable, and be unobtrusive. In the reflection, so a couple of insights that were generated. Academic researchers in particular may deal with the challenge of access to real-world planners to help provide better input to their models. So that's something that we heard. A second question that emerged was, how do we trust AI? You know, we need to develop approaches to define trustworthiness scores and use them for modulating decision-making. The third reflection was the need to create tools for runtime monitoring that emerged as a particular topic for further investigation. And this would allow for a rapid response to system failures. And then finally, there was a gap that emerged through discussion between simulation and real world for assurance. So getting those quantitative safety metrics that are predictive of net real world safety is still very much an open question. So that's something that we would want to further investigate and could potentially generate future work that we would need to look into. So it looks like I am on time. So it is now my pleasure to introduce our esteemed speakers for the discussion portion. And I know I did go through those highlights very quickly as fast as I could, but we will share all of the slides and the recording will be made available as well as the post-workshop report. So I'm now happy to introduce our speakers. We have Dr. Srini Mandalopu, who is a general engineer in the Office of Next Gen at the Federal Aviation Administration. Dr. Craig Thor, he is a chief scientist in the Office of Research, Development, and Technology at the Federal Highway Administration. Dr. Neeraj Kool is chief data officer and advisor for railroad data in the Office of Research, Data, and Innovation at the Federal Railroad Administration. And of course, we have our Haas COE Deputy Director and Chief Scientist, Dr. Taylor Lochrain, and Senior Scientist at Haas COE, Dr. Wafang Yu, joining us. So welcome to our guests. We're very happy to have you, and we look forward to the discussion. I think I'm going to kick it off with my first question would be, what did you all think of this AI assurance workshop? I mean, was it helpful in bringing academic expertise to help increase our collective AI understanding of AI assurance? Any areas that you've identified that we could potentially change? I'd love to hear your feedback. So I'm going to pass it over first to Dr. Craig Thor, if you'd like to lead the discussion.
Sure, thanks. I think, first of all, I think that this workshop has been exceptional. I think bringing all of these different players together, just the breadth of the topics that are presented, I think coalescence around the idea that this is a very important topic, and hearing everyone say that together kind of in the same virtual room, if you will, I think is really important. And it just reinforces the fact that we have a lot to do in this space, but I don't think there's any disagreement that it's all very important. And so if nothing else, as a first step of bringing together these different people from different players from different domains and different sectors who are dealing with the same problems and identifying that, yes, we can work together on these things and we can potentially find some solutions to them, and that it makes more sense for us to do it together rather than a stovepipe fashion. I think this has been really effective, and if nothing else, getting that conversation started.
Great, thank you, Dr. Thor. Dr. Mandalopu, Dr. Kool, feel free to jump in. We'd love to hear your perspective.
So I can go next. So as kind of to echo Craig's thing, I think this has been kind of incredibly useful, bringing these diverse perspectives, identifying the challenges, the complexities involved. And as in one of the key things essentially from a modal perspective is that, hey, AI assurance is one important aspect of the overall kind of system designs to deploy these in practices. So just to understand that, hey, we cannot kind of, well, from an academic point of view, data assurance and then deployment are like individual things and model perspectives. From a model perspective, we're looking towards it. How do we deploy these things? And these are important aspects. So I think even just that realization and kind of getting all these diverse opinions together has been incredibly useful. you asked that how we could improve something. So as in you asked, so I'll say one. I think one of the things is there could be in the future, as in next steps, is kind of bringing some modal perspectives. While there are commonalities among some of these things, there are also unique and different challenges to each of those things. So like kind of focusing on kind of individual ones, maybe an area where we could kind of in the next step focus on, because there I think are unique challenges that are specific to each mode of transportation.
Absolutely. Thank you, Dr. Kuhl.
Okay, thank you. And I echo the sentiments. And as you can see, the technology is evolving day by day, and we are trying to catch up as a federal regulator, and we need to be abreast with these technologies. The only place we can get that aspect is like the avenues that you guys created to exchange the information, to see what's going on and how we can implement those things in our work related activities. And plus, as you can see, FAA has a different kind of needs for assurance and things like that. And that assurance, we've been struggling to supplement with the standards, and existing rules and regulations are not sufficient to assure these systems are safe. So on that way, we need some kind of case studies to bring to the forums, and we understand how those assurance evidence can be brought together, and then we can enjoy that kind of evidence that we can use for the certification engineers to follow through. And in that sense, in our recent FAA assurance roadmap exchange, information exchange meetings, X-Wing brought up a beautiful example of case studies. So that kind of case studies, if you can bring it up, and if somebody explains explain to us what's going on and what are the gaps and how assurance gaps can be filled, and how they can see the newer aspects of these assurance in this AI world, that would be great.
Taylor, Wafong, anything to add?
You're first. Mute.
Oh, Wafong, you're on mute.
I'm also on mute. Go ahead, Taylor.
I was just say, hey, I mean, we kind of brought this together, but the whole purpose is to understand from academia all the different diversity in this topic of diversity of thought, all the different research activities, because I think you're right. Each mode at DOT is going to have to approach this differently based on the perspectives and how they're deploying the technology to service their mission. So I think you're spot on that, some of the next big steps we have are going to be diving into the modal use cases specifically, and really trying to get our hands wet inside, those types of components to look at how we apply AI assurance in all these different perspectives. Wafong?
Yeah, this is really our goal to support our operating administrations. Of course, first we want to learn from you, your needs and priorities, and then build on that. Based on that, we can bring in our academic and industry partners, not only for the technology development, but also help us to figure out how to assess these technologies and how to use them for the assurance, and even in the future, any regulatory effort. So this is really our objective. So we want to learn from you, and we just play in the middle to help to coordinate and collaborate. And of course, our expectation is you always will lead all the different assurance, not only AI assurance, but also other assurance activities. And that is your responsibility, and we support you.
So I think we heard a little bit about the importance of AI assurance research and collaboration across the modes and across, with the academic community and industry, but I want to dig a little bit deeper. So for this next question, Srini, I'll start with you. So based on this workshop, what are your thoughts on AI assurance efforts or relevant efforts like AI safety, data analysis, risk assessment, and so forth as it relates to your agency?
We doing a considerable amount of work, particularly in the assurance area. And we have projects ongoing with Boeing, GE, KBR Technologies, and NASA, and so on. And in these research efforts, we're looking at the assurance technologies. And some of these, there are quite a few technologies available in the market. And Wolfgang was the principal investigator of that particular piece before he joined DOT. And he brought up a lot of these technologies and evaluated them. There are quite a few, some of them good for certain models and some of them not good. And again, the scalability of these technologies is it's not satisfactory at this moment. And regarding the data, we've been working with George Washington University, see the data sufficiency and how we can bring up some kind of a criteria for assurance, data assurance, how good it is, and in the terms of the design domain, and how we can bring up some kind of a criteria to evaluate the training data, whether it is covering all aspects of our operating domain. And also, Dr. Pham talked about it yesterday regarding the overarching properties, which is an alternate assurance framework that we have been working on with NASA. And this is like a domain independent and technology independent way of assuring things. So we're trying to mature that process. And we took up some studies with that, applying the AI/ML functionality and how we can assure those things. And also we're working with KBR Technology to develop a overarching properties assessment framework, how to really develop some kind of a baseline standards to make sure these assurance arguments are properly framed and that kind of work. So there's a lot of work going on, and we are looking forward to publishing these reports soon.
Great, thank you. Neeraj, I'll pass it to you.
Again, just to repeat myself, so one of the things from a modal lens, I see AI as a tool in contents of meeting our mission objectives, correct? So then that AI assurance isn't kind of done in isolation in terms of academia or something saying, hey, we want to solve a problem. And then as part of that problem, AI may be a tool to use it. And we need to make sure that tool kind of has the necessarily performance criteria and is trustworthy, safe, and secure. So in this context, I see kind of this AI assurance falling under three kind of major categories. One is into research and to evaluation and development of AI technologies, which at FRA we've been doing for like a long time now. I have my colleague here, Sam, who is joining. We have funded research into AI, and as part of that effort, as in we evaluate this using standard approaches, validating against a goal data set. But I think the other aspect that we have to then kind of focus on or something is where do we, when we deploy technology, that's the second case. And then the third aspect essentially is when we are leveraging AI to improve our business process as part of doing some things. And I see these three as two major kind of categories. We have some things, as I said, we are mature in some. We are starting to develop or making some early steps on others. The R&D part is kind of something where we are very reasonably mature because we have been funding AI research. Also want to kind of point out was that we have a transportation technology center in Pueblo, Colorado, where we are envisioning some test beds where we can actually do some real world settings and kind of evaluate these tools. That's something we're kind of interested in or would be a role that we have to play. An example could be we introduce what I call as an exception, say a dip in a track, and then see whether these AI technologies can really detect them in a real world setting. So that's kind of one aspect effort that we are on. We also have like some very internal small things about how we use AI internally in practice. I'll give you an example, and why that is challenging is So we have forms that we receive that from which we want to automatically extract information to do some trending. It seems from a technology point, it's a solved problem. So there isn't difficulty in extracting. OCR and PDF extraction has been in industry for years and years or decades now. So what we are internally putting in place are processes where we put our AI, our business SMEs in touch with AI SMEs. So for example, it is not, we need to tell these folks, hey, there could be a concept drift, there could be a model drift. So while you maybe have done it once and kind of figured out that it is working, you are applying these in a real world setting where the underlying form, how it's being submitted, or it may change. Correct. So you need to then make sure what AI assurance, and again, this is not a safety critical system by any stretch of imagination, but this is how we operate or something, saying, hey, go back and make sure you are analyzing these forms through a random sampling or something and making sure you're still, your performance criteria meet your goals. So some of, as I said, some of these are the steps that we are taking in place, and again, the executive order on safe, secure, and trustworthy deployment, along with the OMB guidance, is kind of some of our guiding lights in this regard. So.
Thank you for sharing. That's very interesting. And I like how you put it, you know, AI assurance is not just a tool, it's a critical component of meeting our research mission objectives. It's beautifully put. So Craig, I'll pass it to you for the Federal Highway. Thoughts on AI assurance efforts?
Yeah, I think, you know, in some ways we necessarily have to come at this from a different angle because we are not a regulatory agency. And, you know, we work with all the state's departments of transportation, who are the ultimate deployers of technology and the assets, and they maintain the assets. But they do look to us for guidance. So we do have a very significant role to play in this. And I think as we move forward and we're talking about things like AI assurance, all of the state departments of transportation, the cities and municipalities, you know, they're being sold products by industry and they're being promised certain things about what these products can do. And they're coming to us and saying, how can we trust this? And where do we deploy it? And, you know, how can we assure that this is going to do what they say it's going to do? And I think that's a very important role for us. But to do that, we need to have these kinds of conversations where we're working with our partners, our stakeholders, with industry, with academia, to understand the full breadth of everything that's going on, so that we can provide that good guidance back to them, and we can work with them on developing specifications and you know, those other areas. So I think that's really important for us to think about, and that's kind of the area that we're looking at more and more. One of our initial efforts is to work with states that are already deploying some of these technologies, and some states have been using AI technologies of various types for even a decade now on their networks, and going back and talking to them about, well, how did you assure the safety of these systems, or have you assured the safety of these systems? And if you have, you know, what are your best practices? If not, let's have a conversation about how we can conduct that analysis. And so working with them to see what's already being done, and then seeing where the gaps are, and that identifies, you know, areas that we can help fill in. And I think that's going to be a really important part for us at Federal Highways. And I do want to point out too, for us, it's not just about the connected vehicle space and that the automation space there. We're also using AI in all aspects of our research program. We're using AI for pavement science. We're using AI for investigation of assets. But you still have the same questions. How do we know that if we use a drone to inspect a bridge, that it's actually going to pick up on all the critical components that we want to be concerned about, and making prioritization decisions based on what is identified? All that still requires an AI assurance aspect to it, so it goes across our entire portfolio, not just kind of the connected vehicle, connected automation space. But it's definitely something we're recognizing as a very important area in everything we do. And I think, you know, in another step we're taking and moving in that direction is looking at the NIST AI risk framework through our exploratory advanced research program. We're institutionalizing that on the projects where we are investing in AI applications. And, you know, the real benefit of that, I think, is that we're thinking about a lot of these issues before we even start with the research. We're doing that initial assessment ahead of time and saying, where do we predict that the AI issues might arise, the safety concerns, the equity concerns, bias in the data sets, all those kinds of things, and trying to head those off early on. That doesn't mean we're gonna get everything right from the beginning, but at least we're doing that initial assessment. And I think that's also critical as part of this AI assurance approach, is not just waiting until you've developed something, but before you even start development, what are the things we want to be looking out for? What are the potential hurdles and pitfalls that we need to be aware of? And so working with the Exploratory Advanced Research Program, that's kind of the first step. But ultimately, we want to take what lessons we learn from that approach and apply it across our portfolio more generally. So we definitely recognize this is a very important area. I will say, just like everybody else, we're playing a lot of catch up because so much of this is changing day to day, and there's been conversation, with this also about how it's hard to recruit the right talent, and how do we, educate our own workforce and recruit their next generation workforce, and all of that to make sure that we're in a good position to serve the taxpayers the best that we can.
Yeah, excellent points. And I think we've heard from each of you, Srini, Neeraj, Craig, the importance of AI assurance in your research efforts and for your organization. So the last question, I'm going to ask 20 to 30-second response. What are your interested AI assurance concepts or areas in your future research or work? Srini, I'll start with you again.
Once again, we have various design assurance levels, A, B, C, and D, and we are nowhere close to B or A, and we are trying to limit our works because of this trustworthiness of the A system. So the next level would be targeting that level B systems and level A systems, which is going to be really challenging to do.
Neeraj?
I think, again, coming back to how do we kind of get all these things together? Again, this is an interest in terms of a framework where how we need to deploy these AI applications in practice, kind of going across all the aspects that were deployed. How do we kind of compare safety critical systems versus the others? Is this AI assurance needs the same? Do they differ? I think that's an area of interest, at least from my point of view.
Thank you. And Craig, if you could wrap up the discussion.
Yeah, I think a big question for us right now, as I said, AI, I keep saying we're not necessarily asking for AI solutions in our research proposal, when we send an RFP, but we're getting AI solutions because that's what the industry is seeing as giving it the most effective result. And so that being the case, we need to be, I think our priorities right now are being educated enough to understand what it is that we're dealing with, what are these systems, and then also ultimately figure out what is our role within all of this. I think that's a big question for all of us, and definitely at Federal Highways, is that where do we see ourselves in this space? We're not going to be the ones that develop all of these systems, but we are going to be the ones that are ultimately responsible for making sure that they're safe and equitable and all of those things. And so working within industry, our partners, the other modes, and trying to see what is our space, how do we develop a roadmap that's going to help us be successful, and so that we can also enjoy the benefits of these technologies, right? There's a lot of possibility here. We want to make sure that we're leveraging that in a safe way.
Great, thank you. Wafong and Taylor, I want to give you an opportunity for any final insights or comments.
Yep, I'm good. That's the last Taylor.
Great.
I think this has been great, and I appreciate everybody's time today. So Denise, we're gonna pass it to you. We're gonna head over to Ian for our final.
Great, yes. So thank you, everyone. Big thank you to our speakers for the insightful discussion. I'm now going to hand it over to Ian to conduct the final poll. If you have any questions, please feel free to reach out to haas-coe@dot.gov. We will be sending communications following the workshop. So Ian, all you.
Thank you. All right, so one final poll question, question 18. So based on what I learned from this workshop, I am now more prepared to apply AI assurance best practices in my work or research. So we have another statement question, last statement. Just go ahead and please indicate if you agree or hopefully agree or disagree. And I'll start a timer for 30 seconds. You should be able to answer.
We saved the best question for last. see how much you guys have learned over this period. So best question for last, everybody. Let's get those numbers up there and let's see, was this productive the past few days in learning more about AI assurance to help us really make some good decisions on where to start, what other questions we want to start asking with our stakeholders and partners and colleagues. So please take a moment.
All right, so our initial returns are good. More on the left than on the right, always good. So we have a lot of people somewhat agree and a few strongly agree. A few on the right side, but for the most part, somewhat agree, which is always good. So I just want to wrap up the questions. Thank you everybody for participating. I'll turn it back for the closing.
Well, thank you, everybody. I really just wanted to thank everybody today. Also like to ask Trung Pham to join me on screen, and Bob Sheehan, please join me on screen if you're online as well. Just again, wanted to say what a really insightful couple of days that we've had here. Bob, Trung, any final thoughts from either of you?
Yes, I'm really excited to see everybody come together and agree to work on the same problem that has been a major problem that we never had solution before. So far, we had a lot of discussion, but in this meeting, it seems like we identified not just a technical problem, but also the funding situation and so on, that will help shape the path moving forward. And I'm looking forward to see more meetings like this in the future, where we can bring everybody together from different perspectives to work on the same problem that we have the same common interest to solve. So in that aspect, I just want to take a minute to announce that at the FAA, we normally have regular technical exchange meeting to talk about AI regulation and the technical challenge in that aspect. And so far, we had quite a few meetings with big participation from everybody that we could send out invitation. So the next meeting, we are planning to have it around the end of July, and we are looking for the proposed location in McLean, Virginia, where our contractor MITRE will be organizing. As soon as we have the confirmation, we will ask DOT for help to reach a wider audience. And the next topic of the meeting, the topic of the next meeting is to show the community real example of AI application, not just about what it can do or what is the research problem, but the real example is about how we certify or approve those products in the past. And one of the things that I heard from Professor Fan from MIT is that sometimes we need to see the real project. So in the next meeting, we will bring in the new project. We will show what are the requirements, design requirements, to work through the design process and to walk everybody through the approval process that we already did in those projects. One of the projects that people heard a lot is the ACAS-X project that has a machine learning component. So we will walk it through, show how our counterpart EASA from Europe certify it, show how the FAA concur with that certification, and then we will show a few more research projects that we funded and show the example of the requirement and the verification of the requirement in the design process. that correspond to what we discussed today about design assurance. And that will be the first step before we move forward to more question about operation. Thank you.
Thank you, Trung. I think that's really exciting to hear, and look forward to learning more details about that upcoming FAA workshop in the near future. Bob, over to you.
Thanks. And it's always fascinating to speak about a bunch of people because I could say a bunch of stuff, or I could say what they said and drop the mic, as others may have done. But I am going to repeat some things that I already said. And I think it's great because that means we're on the same page. So our intent is to move forward with action, and I want to be more specific than just the generic statement. So in addition to the community of practice, called out by Phong, we plan to engage implementers and practitioners in a similar way, hopefully or possibly through pooled fund studies and other efforts to bring those practitioners in, so that we can take not just examples of some state DOTs that tend to be on the front edge of some of the work, but the others who are interested, and they may not be on the bleeding edge, but they're interested in moving forward. So that's one effort we want to do. So this also allows us an opportunity to address more completely the full spectrum of potential applications that we talked about before, and just was highlighted in the last panel. And so it brings in the potential applications and the perspectives by different modes, focusing on the overarching objectives and performance requirements, and not necessarily just the doing it research in AI for just the sake of doing it. So because that allows then bringing the other modal partners into the work. So this is what I think Craig was getting to this as well. We are conducting our research and development activities with the end in mind. Well, that's the intent. So applying reasonable system engineering, reasonable scientific method. For me, I would call it engineering 101. What is the need? And then it drives the research. And now in this case, it's incorporating the implementation, the evaluation, and the assurance needs and activities in the full cycle of our work. So that when we say, hey, this is a different need than deploying a simulation tool that is a little bit better understood, or you can understand the data in, the data out, and actually what happened, we may have to apply different methods and approaches for this type of work. Lastly, and specifically, as Craig also stated, that we're moving forward with work to address some of the challenges, perhaps calling them the boundaries or the guide rails with respect to risk, capability, and assurance. We are working actively with an internal working group to build our capacity monthly to make sure everyone has a better understanding of what is and what is not in this area. Developing a methodology and a framework for our federal investment decision making. That's one of the things I was trying to make a point a few hours ago, is understanding where is the federal role in some of this work to support implementation, and as that may be on the work to support testing or certification or data sets that are available and for others. And so then that brings us to the other words. We are working with our model partners to develop a collaborative plan for investment, and that's the key. We all work together because every one of us brings something else to the table and some expertise. And so that's the current focus right now, and we're having to be in that time frame where that is occurring as we, with our federal investment and time and fiscal year, we're moving into that planning phase for next year and the following years. So I'll close with thanks to the team that delivered and developed the workshop, and then thanks to everyone who participated and great notes, and we're taking those things, really incorporating the input into our work. So very much appreciate it.
Thank you, Bob and Trung. I think I couldn't have said it better myself. We're really, really grateful to the folks, for all the speakers who prepared this material, for all the folks behind the scenes. I especially wanted to thank Wafang Yu, who really started this work stream at the Haas COE and has really just continued to champion this concept of AI assurance in the organization. Wanted to say big thank you to the Haas team who supported us. A big thank you, Trung, to the FAA, to the ITS JPO, to the Federal Highway Administration, to the Volpe staff behind the scenes, that made sure that everything went smoothly here today. You can see here, we're going to be posting the materials online at the link that's on your screen right now. There's going to be another session in this line of work that will take place this fall. Everybody on the distribution list for this event and who attended this event should be receiving that. Also, of course, we have Denise on screen here. She'll show a slide here in a moment with a place that we can ask any follow-up questions. This really has been inspiring as a day for me. There's nothing that does my heart good like watching researchers and regulators work together. Really is inspiring. And in this task of reviewing, assessing, and validating automated systems, I think this has been a really big step along that path together. And we need to continue finding ways to work together, to share knowledge, and to learn together. So thank you all, and look forward to seeing you soon. Denise, please go ahead and close us out.
Great, and that wraps up our USDOT AI Assurance Workshop. I want to again extend a major thank you to all of our speakers, moderators, and our wonderful and engaged audience. Your voice and involvement is truly critical to driving this research forward and ensuring AI assurance for safety and transportation. So we want to continue to hear from you. Please don't hesitate to reach out if you have any questions. I've included our email on this screen here. You can also explore our website where we'll be periodically posting new content and announcements for upcoming workshops. Any other engagements, materials will be posted there. And look out for an announcement for our next workshop this fall. We'd love to see you there. So we'll be sending communications in the coming weeks to months here. So thank you again for attending and have a great rest of your day.